Hello friends, welcome to our channel Knowledge Amplifier. So in this particular video tutorial, we are going to explore a very important open source storage framework, and that is DeltaLake. So as you already might be knowing that DeltaLake generally support ACID transaction on top of our data lake, and that data lake can be in any cloud platform. For example, it can be in AWS S3 or Azure Blob Storage, etc. etc. Generally, while working with this kind of data lake system, a common problem is we cannot simply perform insert, update or delete in the data lake files directly. For example, suppose you are having one S3 CSV file stored and we need to update 2 rows in that CSV file. Generally, what we have to do, we have to read the complete file using pandas or PySpark and then update those specific rows in pandas or PySpark data frame and override the data in the existing S3 location, right? But instead of that, if we can have an additional layer on top of our existing data lake which support this kind of insert, update, delete, this kind of operations, that would be great, like how we generally do in database or data warehousing systems, right? That is already the advantages of data lake will be available. Along with that, the advantage of data warehouse, that is ACID transaction, etc. also, if we can get somehow, that would be great in designing complex data pipelines, or in case of building transactional data lake, that would be great. So there Apache Hudi, iSpark, DeltaLake, etc. systems comes into picture, and DeltaLake is one of the such open source storage framework which can sit on top of your existing data lake and provide a ACID functionality on top of your data so that you can perform insert, update, delete, etc. So in this particular video, we are going to explore the fundamental concept of DeltaLake with practical examples. So here I am going to show you the demo with Glue notebook. So this notebook link I'll be providing in the description box. You can just copy the code and make it ready in your AWS account as well, so that when I will be explaining the demo, you can parallelly practice with it. Okay, if you run the code, if you change the code, try to understand how it is behaving, you will be always getting a better idea out of it instead of only watching the video. So to start the demo, first obviously I need to have a role which this particular notebook will be using. So for that purpose, here I have created IAM role, modern test, and here I have provided these 3 access, Amazon S3 full access, Glue console full access, and IAM full access. Okay, so here with that basic configuration, we are good to start with our first cell, where we need to configure certain properties to work with Delta table in Glue notebook. That is, if you see, first thing, Glue version and ideal timeout are default configurations here we are putting. That is Glue latest version you use, that is Glue 4.0, and ideal timeout is 60. That is, if continuously for 60 minutes there is no activity in this notebook, you please stop this notebook to avoid unnecessary cost. Okay, right? Then these 2 configuration we have to give to work with Delta table. Number 1 is Spark SQL extension is DeltaSpark session extension. This is very important. And apart from that, the Spark catalog we have to configure as Delta catalog. Obviously, I hope you are getting it that whenever we want to create some tables, the catalog basically helps to store those metadata information, for example, the column names, column data type, etc. So while working with Delta table, we have to make sure we are mentioning this Spark catalog, it has to use Delta catalog. Okay. And data lake file format we have to configure as Delta to work with Delta table. So with this basic configuration, we are good to start. So in our next videos, I'll be showing you in detail on how to work with Delta table and PySpark or Python. But to keep the first demo very simple, I am going to show you the experiments with SQL query so that you will be getting most out of it. So to work with SQL and Glue notebook, just you have to use this magic command %SQL. That way Glue notebook will understand that we are going to execute SQL query, not Spark query. Okay. So first what I am doing, I am creating a database if not exist, to show you this particular POC. Now as part of the next step, I am going to create a CSV table pointing to one of our data lake paths. If you see, DeltaSpark testing is the bucket name. Within that, ID's data is basically the folder name. I have already created this bucket DeltaSpark testing, within which we are having the folder called ID's data. And here if you see, we are having 4 files. And if you are from data science or data engineering background, you might be already familiar with this particular data. That is, it generally is having 5 columns. For example, ID, sepal length, sepal width, petal length, petal width, and class name. And it is having 3 classes, 𝒃𝐿, 𝑑𝒕𝒂, 𝑑𝒕𝒂, and 𝒂𝒂𝒃. Along with that, I have added another class with the class name another category, and it is also having that default schema, that is ID, sepal length, sepal width, petal length, petal width, and class name. Okay, just to show you the demo more intuitively. Okay, nothing else. Obviously, you can perform the same demo with these three class of IDs dataset as well, not a problem. So as a first step, what I am doing, I am going to create a CSV table pointing to that particular S3 location. A very simple stuff. Now let me just tell you what I am trying to achieve here. So I am already having some CSV files, one particular S3 location, that is this particular location. And I have created one CSV table pointing to that particular location. This is obviously one external CSV table, right? Now what I am trying to do, I am trying to create a delta table. Okay, and to have delta table in our S3 data lake, we have to store the data as delta file format. So how delta file format looks like, that I'll be explaining you after some time. So as of now, our primary objective should be converting the CSV file to delta file. So generally how we convert any particular file format to another file format using Hive tables, that same concept I am going to follow. So in this case, what I'll be doing, I'll be having another S3 location. Maybe here if you see, the folder name is IDs data, and here I can give the folder name as delta-data. Okay, pointing to that same bucket. Okay, just DeltaSpark testing and then delta_data. In this particular location, initially this will be an empty location. Pointing to this, I'll be creating one delta table. Like here, how I am mentioning using CSV. In that particular external table creation, I'll be using delta. Instead of CSV, I'll be writing delta. Okay, so that way, pointing to this particular new folder location, one delta table will be created. Now this particular folder location is empty. Actually data is available here, but not here, right? So I'll be just executing a insert into command from this CSV table to the delta table. So that way, automatically, because this is an external table, it need to store the data in some external stage, that is basically this particular location. So automatically it will be storing the data in this particular location as delta file format, because while creating this particular table, we have configured that this particular table should be of format delta. Instead of using CSV, we will be using delta as a command in this particular place. So that way, easily from CSV, we will be getting delta format data, which will be stored in our same S3 data lake. Okay, right? So I'll be deleting this and going back to mouse pointer instead of pen, and let me go to the next step. So here you can see our CSV table is already created. Now if I just view this data by applying a simple select query pointing to our CSV table, we'll able to see our default IDs dataset, that is ID, sepal length, sepal width, petal length, petal width, and class name. If you want to observe what are the distinct class names are available, here you will able to see that it is having IDs 𝒉𝒐𝒂, IDs 𝒉𝒐𝒂, ID 𝒂𝒐, and also another category. As I told you, I have just created one more dummy category, right? But one point to be noted, here in this particular bucket, apart from IDs data, there is no other folder available. Okay. Now what I am doing, I am going to create a delta table. So as I told you, this time I am mentioning another location within the same bucket, but the folder name is different, that is IDs data delta. Basically, it will be storing the delta formatted data. Okay. And while I am creating the table, I am keeping the same schema as of our CSV table, but this time the format I am mentioning using delta. So that way, it will be treated as a delta table instead of a CSV table. And then using spark.sql, I am executing the query. As simple as that. Okay, right? So here, let the query get executed. So here it is done. Now, if you want to see what are the tables available in our database, you can just execute this command, that is use our database and then show tables. You will able to see two tables. One is CSV table, one is delta table. Even if you want to confirm, here you can go to data catalog and then database. Here you will able to see that we are having our database, that is whatever we have created, that is DeltaLake DB. Within that, two tables will be there. Let me quickly show you. So here DeltaLake DB, and within that CSV table and delta table is available. Okay, right, perfect up to this. And now what I am doing, I am executing a select star command pointing to our delta table. So obviously we just created the table. There is no data, right? So delta table will be empty. Now I am executing insert into delta table, select star from CSV table. So now what will happen? Automatically CSV data will be ingested as a delta data pointing to our another folder whatever we have configured, that is ID's delta data. Okay, if I refresh, currently here you can see that already 2 folder is created. Okay, ID's data delta. Why it is created? Because here we have executed this particular command, create table, right? And this is pointing to this location. Now this particular folder was earlier not available in our data lake, but now it is created due to that create table command. But if you go inside that, here you will able to see 2 folders. Now this is a very important part. That is delta table, whenever you create or whenever you try to store the data as a delta format, it always has 2 components. One is actual data, one is transactional log. Transactional log basically getting stored in _delta_log in this particular folder. It will be storing that whatever activity you are doing. For example, you are doing some insert, update, delete, etc., etc. Whatever you are doing, it will be keeping a track of all those transactions in this particular folder. And then obviously when we will be ingesting data outside this particular folder, the actual data will be stored. Okay, so let me go inside this particular transactional log folder, and here as of now you will be able to see only one JSON file. If you download that, you will able to see the detailed transaction log related to this particular table. And obviously I hope you are getting this, that as of now we have not performed any operation. So in this particular transactional log, it will only have that the user has created a create table command, something like that. So here if you see that commit info timestamp operation as create table, that means the user has done a create table command. That's it, nothing else. Okay, the format or schema, if you want to observe, that also is obviously visible with this metadata information like sepal length, sepal width, petal length, petal width, their data type, nullability, all things are available here, right? So this is our first transactional log what is available, but because there is no data, that's why outside this particular folder there is no information. Now what I will do, I will execute this insert into command. Okay, so here you can see the command is getting executed, and here you will able to see that automatically data will be getting saved here. And here is the beauty, 4 Parquet files are created. Okay, maybe delta table in the backend working like this way, that we are having 4 classes or 4 CSV files. From that it is converting to 4 Parquet files. Maybe you can think like that. Okay, so there are 2 very important points, as I told you, that Delta Lake always store 2 important things. One is actual data, which is stored in our normal folder location. Another one is transactional logs associated with the delta table operation, and those getting stored in delta log folder. So obviously we have executed one insert command, so one more transactional log should be created. So we should able to see one more transactional log within this folder, and here you can see there is a new JSON ending with 1. If we download this particular JSON data, we'll able to see, we'll have this information that in this particular transaction, these 4 files is inserted. That way it is basically keeping track of all the insert, update, delete. So here if I open this one, here you will able to see that this is an add activity. What it is adding? It is adding this particular Parquet file. So what is this Parquet file? If we check, if I just do a command if, that is basically this particular Parquet. Okay, then another add activity is this particular Parquet file. If I do a command if, here this one, then another add activity is available here, and this is the Parquet file. So here you can see, and then the 4th add activity is available here, and this is the one, and here you will see. Okay, so that way I hope you are getting the main point, that in the latest transactional log, whatever addition we are doing due to insert activity, those are available. So obviously I hope intuitively you are getting that if we perform some delete activity, that also will be available in another transactional log, that maybe one particular Parquet file is deleted, something like that, right? Not only whatever files are getting added or deleted it store, but it also stores statistical information of that particular addition or subtraction. For example, this particular Parquet file, if I just have a track, maybe in this Notepad++, I'll be having a track. So this C00, if we observe this one, right? This one, if you observe, for this, these are the stats. That is, number of records are 51. Minimum value for the ID is this much. For sepal length is this much. Sepal width this much. Like that, lot of informations are available. And in this particular file, the class name, whatever is available, that is only ID is _𝒔𝒆. Okay. So I'll be keeping a track of this also. Later this will be useful, that this particular Parquet file is containing only ID's particular class. That information we are getting from this metadata. Obviously you can download and validate whether it is true or not. So I can download and show you in some online Parquet viewer, because I cannot directly open the Parquet file. So here I'll be going to downloads, and this is the Parquet file. I'll open this one, this processing. So here you can see this is the data and the class names are ID's particular. If I scroll below, you will see everything is related to ID's particular, and that same information we are getting from this statistical information from our transactional logs, right? So I will be completing this mapping because later it will be helpful. So now this particular Parquet file is related to ID's 𝒕𝒂. Then another Parquet file, if you observe this one, is having the class of another category, whatever we have created as a dummy class. And the last Parquet file, I guess it will be having ID 𝒂𝒂, because that only is remaining. So yeah, and here if you observe, this is ID 𝒂𝒂. Okay, right? So as of now, in our delta table, all these 4 Parquet files are contributing. If you query your delta table, all these 4 Parquet files will be required to return the data. Okay, right? That's what it is signifying. Now what I will do, I can simply executing select start from delta table limit 10. Here you will able to see the same data, whatever we were earlier able to inspect for CSV table, right? But initially when we executed delta table, that time no data was there. Only post insert command only the data is visible, which is obvious thing. And again, if you execute select distinct class name, you will be getting all 4 classes, ID 𝒂𝒂, ID 𝒕𝒂, ID 𝒕𝒂, and another class. Okay, now let's see the main beauty of our DeltaLake, that is we can perform insert, update, delete on top of our S3 DeltaLake. For example, if I just simply give you this 4 Parquet file, and if I ask you to delete something, you cannot simply delete. You have to read the whole data or whole folder in PySpark data frame and delete from that data frame or filter that specific data and then override the rest of the data points here. Instead of doing all those things, DeltaLake is helping us to execute insert, update, delete command pointing to this location. So that will inspect. So now what I am executing, delete from this particular table where class name is ID's 𝒕𝒂. Okay, right? So that will inspect how it is behaving. Before that, let me open DeltaLog in a new tab. So as of now, only 2 transactional informations are available. One is related to create table command, one is related to insert command, whatever operation we have done in our DeltaLake, right? Now we are executing a delete from this particular command. Okay, so that way the Parquet file which is containing this ID's 𝒕𝒂, that will be deleted. So that will inspect how it is behaving now. So before going to the S3 DeltaLake, let's inspect that whether it is really deleted or not. So if I execute select star from our delta table where class name is ID's 𝒕𝒂, we will be able to get nothing, because we have deleted the ID's 𝒕𝒂 class from this delta table. So how it should behave? First thing, in our transactional log, we should be able to see one more JSON which will capture this particular transaction that something is deleted. And here you can see this JSON is available. Okay, so let's download this and let's see how it is behaving. So here I'll open this one, and here you can see earlier we were seeing add activity due to the insert operation, but now we have executed a delete command, so we are seeing remove operation. And here if you see, out of these 4 Parquet, ID's 𝒕𝒂 is available in this particular Parquet file, right? So we have executed delete from table where class name is ID's 𝒕𝒂. So that means this particular Parquet file will be removed from our DeltaLake table. So let's see whether in transactional log same thing is displaying or not. So I'll just search it, and maybe I'll be clicking on up. So here you can see the same Parquet file is removed, because this Parquet file was containing information about ID's 𝒕𝒂. That's why this particular remove information is available. And there is another activity it is showing, that is add. So maybe it has added some new Parquet file. I'm not sure. Let me just have a cross check. Ideally, there is no new Parquet file should be created for delete operation, because here we already have this 4 Parquet. We are just deleting one particular Parquet file which is not needed. So from S3 by default quickly it don't get deleted. Obviously it will persist for a certain amount of days. Later I'll be discussing that particular configuration. By default in DeltaLake, if at all any file is not getting utilized due to delete command, it will stay for 7 days, and post 7 days only it will be deleted. That is, if you observe this particular file, whatever we have executed as a delete command, and due to which this particular file is detached, now immediately it is not getting deleted. If I refresh, here you will be able to see that this particular Parquet file will still be there. It will be there for 7 continuous days, and after 7 days what will happen? Automatically this will be deleted, because this is not contributing in our delta table data. So I hope that concept you understood. But let's see why this particular new Parquet file is created. That is another point of query. I'll just have a command def, and here you can see this is a new Parquet file which got created. If I just sort based on time, this is the latest one. Earlier files were created at 9 p.m. but it is at 9:16 p.m. So maybe what I can do, I can download this particular data and inspect what is having in our same Parquet viewer. Okay, so there is no rows available. Maybe it is created for a dummy purpose, but I hope you are getting the point. Even if you check the size of the file, earlier files were of 2.4, 2.2 KB, but this is 756 bytes. So adding this particular one in our DeltaLake table does not make any sense. Maybe DeltaLake for some internal purpose is adding this, but we can ignore this. I hope the major point you understood, that it is detaching one particular file which is no longer needed due to this delete command, which generally you cannot perform in any S3 data lake, that you are able to do using DeltaLake. And we have executed this select command also, and we have verified that 𝐼𝐷 is deleted. Okay, now what we are going to do, we are going to execute an update command. So I'll just zoom this particular part little bit, and what we are doing here, update delta table, we are setting class name equal to testing update, where ID is greater than 20 and ID less than 30, or ID greater than 104 and ID less than 110, and class name not equal to another category. So from SQL point of view, what I'm trying to say, it is a very simple thing. If class name is not equal to another category, and if the ID is falling under this range or this range, then update the data with testing update as a class name. Now let us try to understand or try to think about the output, what ideally we should get, right? So class name, what are the class names we were earlier having? These 4. Out of this, 𝐼𝐷 I have already dropped using this delete command, right? So we are currently having 3 classes, 𝐼𝐷 𝐶𝐻, and another category. That also I can show you. Just I'll be copying this and select distinct class name from this particular one. Okay, right? Okay, sorry, this particular where clause we no need to give. And in this table, as of now, we'll be having only 𝐼𝐷 𝐶𝐻, and another category, right? These 3 classes. Okay. Now, when I'm saying class name not equal to another category, that means only impacted classes will be 𝐼𝐷 and 𝐼𝐷, right? And among those also, if the IDs are falling under this range, then only update the class name with testing update. Okay, so I hope the query you understood. Now I'll simply execute this update command. And here you can see number of affected rows are 14. Now we'll observe what is happening in our data lake. So here again I am in my data lake. I'll just minimize this little bit for easy understanding. So here earlier we were having 3 transactional log, one for create statement, one for insert statement, one for delete statement. Now if I refresh my screen, one more statement should be generated which is related to this update activity. And let us download this particular JSON transactional logs and let's see what is happening here. Okay, so this is the transactional logs. Maybe I will copy this and open in Notepad++ for easy understanding. Save as JSON, maybe I'll save .json all types and I'll save this. So that way the JSON data will be visible in a better way. Let's observe the first operation. What it is doing? It is removing something. What all things it is removing? It is removing this particular Parquet file. What this Parquet file we were having? Let's see. If I just do a command def, this particular Parquet file is related to 𝐼D_SETOSA. Okay, that one it is totally removing. Another Parquet file it is removing, and that is related to this one, which is related to 𝐼D_SVRGNICA. As I told you that two classes will be impacted. One is 𝐼D_SETOSA and 𝐼D_SVRGNICA, and DeltaLake has detected in an intelligent way that these are the two Parquet files where this 𝐼D_SVRGNICA and 𝐼D_SETOSA classes are available. That's why, because those are getting impacted, it has simply removed and it has added two new things. So if you see this particular Parquet file, it has added. So we should able to see those Parquet files here. If I refresh and if I just sort based on last modified here, and if I do a command def, this is the first Parquet file. So let us download that and try to inspect using Parquet viewer. So how this VRGNICA file looks like, let us try to understand. Okay, so the class names are 𝐼D_SVRGNICA, and if I scroll below here, you will able to see testing update. Why it is testing update? Because here, if you observe the query, here we have ID greater than 20 and ID less than 30, right? Maybe in this particular file that is satisfied, that is ID greater than 20 starting from 21, it has updated, and ID less than 30, that is why up to ID 29, the class names it has updated to testing update from 𝐼D_SVRGNICA. Okay, that is how it is working. That's why this new file it has added. So overall what is happening, I am trying to tell you, is one particular Parquet file was having only data related to 𝐼D_SVRGNICA. Now suppose there were 50 rows. Out of 50 rows, maybe only 10 rows would have been impacted due to those update statement. So what DeltaLake has done, it has detached the whole VRGNICA Parquet file from our DeltaLake table, and it has created a new Parquet file for our DeltaLake table where those unimpacted rows are there. Along with that, the updated rows which are having new class with the name testing update, those also it has kept, and that's how it has added this particular Parquet file. And if you observe the next Parquet file, same thing is basically going to happen, but that class will be SETOSA class. So here if you see, this is the Parquet file. If I download and if I refresh, if I upload this particular data, here you will be able to see the class names are SETOSA, but here some testing update class names are there. And why it is happening? Because maybe this particular clause is satisfied, that is ID greater than 104 and ID less than 110, that is ID greater than 104, that's why it is starting from 105, and ID less than 110, that's why it is going to 109. In between that, all class names it is updated to testing update. And same thing happened for 𝐼D_SETOSA file. Earlier we were already having a Parquet file which is having all the class names as 𝐼D_SETOSA, but because we have updated that particular Parquet file, it has detached, right? And it has created a new Parquet file, that is this one, where all the unimpacted rows it has kept as it is, right? That is, these rows are not at all impacted. It just kept as it is, and also the impacted rows or the updated rows it has given. Okay, so that's why here it is an add activity. And the last one is just a simple commit information that user has executed this update command, and the update command is related to this ID greater than 20 and ID less than 30, or ID greater than 104 and ID less than 110, and class name not equal to another category. That is, whatever things we have executed in SQL, that same thing it has tracked. And these are very vital information for audit and reconciliation purpose. But overall, I hope you are getting this, that why two remove is happening and why two addition is happening. One remove for 𝐼D_SVRGNICA, one remove for 𝐼D_SETOSA, one addition for updated 𝐼D_SVRGNICA, one addition for updated 𝐼D_SETOSA. As simple as that. Okay, right? I hope the update activity also you are getting it. Now, if I execute select distinct class name, what will be getting? Obviously, 𝐼D_SETOSA, 𝐼D_SVRGNICA, one more new class, that is testing update, and one more was earlier itself existing, that is another category. So all will be visible. Okay, so if I execute now here you will able to see the 4 classes. Even instead of SQL query, you can directly read the DeltaLake data. That is basically this particular folder if you want to read. Here we are having lot of files. Some files are not at all contributing in our DeltaLake table. Some files are contributing. No need to worry about those management. DeltaLake will automatically manage that and will only show the latest data based on the transactional logs. Okay. So how to read the data in Spark? The command is this: spark.read.format delta. Like generally how we define spark.read.format CSV or format Parquet, etc. Same like that way format delta. And this is the DeltaLake path we have to give. And if you execute select class name distinct show, you will able to see the same output whatever you were able to see using SQL. Nothing new. Now one interesting question let me ask you, that is, what are the files contributing to this particular data frame? Suppose that question is asked after doing all this transformation. What are the files is basically used in this Spark data frame? What will be your answer? Pause the video, try to think for a minute. I am explaining here. So here if you see, in our current transactional log, this particular Parquet file and this particular Parquet file is added. So obviously these two will be contributing, no doubt on that, right? Apart from those two, another file if you observe here is another category, whatever this particular Parquet file we were having right since beginning. This particular Parquet file is not at all touched. That is, we have executed delete command, update command, but this Parquet file was not impacted because this was having the class another category which we never used in our transformation. So this particular Parquet file will also be contributing. So in short, I can say this particular Parquet file and basically these two newly added Parquet file, they are contributing in our current Spark data frame. So we can verify that as well. If you want to observe intuitively from PySpark.sql.functions import star, and we are reading the DeltaLake data and we are selecting the class name, also along with that the input file name we are reading. Okay, using input file name we can basically understand that a particular row in a Spark data frame is coming from which particular S3 location, right? That we are displaying. So if I just run this one, here you will be able to see this data. First thing, another category, as I told you that this particular Parquet file will be there, right? This same Parquet file if you observe, if I do a command def, here this one, right? As I told you, based on our intuition itself, we are getting this, that this should be available. That is, this should contribute in DeltaLake data. Apart from that, here you will able to see this particular Parquet file. Okay, ending with DACE4. This should be related to 𝐷_𝒆𝒕𝒂. That means this is available in our newly addition file. If I execute find next, here you will able to see, correct? And not only in this file 𝐷_𝒆𝒕𝒂 is available, we have also observed that testing update is also available. So DACE4 somewhere available here. Yeah, you can see that same file is available here, and 𝐷_𝒆𝒕𝒂 is another Parquet file. If you copy this particular Parquet file and try to do a command def, here you will able to see this particular Parquet file what was added in our last update command, that also it is coming. And the last Parquet file is basically the same what we are having here, right? So 3 Parquet files, one which is not at all impacted, another 2 are basically what newly added, right? So overall I hope you are getting this, that due to delete command one particular Parquet file was dropped, due to update command 2 Parquet files were dropped, and overall we are having here lot of Parquet files. If you observe 1, 2, 3, 4, 5, 6, 7 Parquet files, but ultimately when you are reading the DeltaLake data, it is having only 3 distinct Parquet files contributing in this Spark data frame data. And DeltaLake using transactional log automatically tracking all these informations. Okay, so 2 very important information, that DeltaLake store transactional log as well as actual data. Actual data is stored in Parquet file format. Transactional logs are stored in JSON file format, right? Obviously, you can execute normal commands like df.columns. Here you will be able to see the same information, df.show, and all other Spark data frame operations you can perform on our DeltaLake data. Okay, right? Now, another very important part, that is historical tracking. DeltaLake also support tracking of all the operations. For example, if you just execute describe history, then your DeltaLake table, it will show you all the historical operations, whatever is executed. So here if you see, these all operations was done. Just minimize this so that we can observe in a better way. Starting from the last row, here you can observe the version and the timestamp. This is the oldest timestamp 1536, then 1539, then 1546, and then 1553. Right? So observe the 1536. First time when we have created the table, that's why it is a create table command. Then at 1539, we have written some data using insert into command. That's why it is an append activity. Then as part of the next step, we have executed a delete command. That's why it is showing a delete command here. And then as part of the last step, we have executed an update command. That's why it is showing update command. Right? So this is how everything is getting tracked, version and timestamp, this information. And also just like Snowflake, DeltaLake table also support time travel. That is, you can go to past, obviously within the limit. Like for example, if you have configured DeltaLake retention period is 7 days, that means the unused files, whatever is available currently in our data lake, those will be only be available for the next 7 days. After 7 days, automatically the unused files will be deleted, right? But within 7 days, if you want to perform a time travel and go back to the old state, that you can achieve just like Snowflake. For example, if I execute select star from our DeltaLake table, and this is the command to go back to any past version, that is version as of 0 if I execute, you will able to get in the beginning version, that is when we just created the table in that particular layer. There we were having no data, right? So if I execute spark.sql query, we will able to see nothing, because that time we just executed create table command, nothing else, right? But if you execute version as of 1, here you will able to see the data, because in the version 1, that is in the second activity, we have inserted the data in it, right? This is the write activity. So if I just execute version as of 1, here you will able to see the complete data. ID is 𝒕𝒂𝒏, ID is 𝒕𝒂𝒏, ID is 𝑑ataFrame, another category everything. Like that way, you can go to past. So if I just show you select distinct class name as of version 1. In version 1, we were having all the classes, IDs, 𝒕𝒂𝒏, 𝒕𝒂𝒏, and another category. In version 2, basically when we executed the delete command, right? That time IDs 𝒕𝒂𝒏 was deleted. So as of version 2, if I execute, automatically the 𝒕𝒂𝒏 will be going away and will be having only these 3 class, that is 𝒕𝒂𝒏, another category, and 𝒁𝒆𝒓. And if we execute as of version 3, there obviously 𝒕𝒂𝒏, 𝒁𝒆𝒓, and another category was there, but we have executed a update command where we have updated the class name for few rows to testing update. So if you execute this command version as of 3, you will able to see another class, that is testing update. Okay, and version 3 is basically our current version. So by default, if you don't mention any version, it will refer to the current version obviously, and it will show you the same result as of version 3, that is these 4 classes are available, right? Obviously, instead of SQL query, if you want to perform using Spark, that also you can do using this particular command, spark.read.format delta, and then option version as of 1. That is, you have to use option version as of, and then you have to write the version number to which past version you want to go. And same load command you have to use pointing to your DeltaLake data in your S3 data lake. Okay, so here we are going to version 1. That means we just executed the insert command post table creation. So only IDs 𝒕𝒂𝒏, 𝒕𝒂𝒏, and another category will be available. Suppose I am executing version as of 0 in this same command. So what will happen? Version as of 0 means version 0 is that time when we just created the table. We have not executed any insert command, right? So class name will be nothing because there is no data. So if we execute select class name distinct, we will be getting empty. Okay, sorry, here it will be df previous 2. If I run it, here you will be able to get class name, right? So I hope in short you understood how you can perform time travel in DeltaLake using SQL as well as using PySpark. Okay, right? So this way DeltaLake store the data. I hope the fundamental concept related to insert, update, delete are clear to you. So obviously each time whenever you do some certain transaction, it will be creating a new transactional log with the JSON extension. Okay, and obviously if lot of transactional log gets accumulated, ideally the value is 10. Post 10 transactional logs, it will compact and it will be creating a Parquet CRC file. That maybe I'll be showing you in some other demo. And another operation which we'll be observing in our upcoming video is, here lot of Parquet files are available which is no longer used by our DeltaLake, right, because of delete or update activity. But still those files are available, and because of which we are able to perform time travel. But beyond a certain extent or beyond a certain timeline, maybe 7 days, 20 days or 100 days, that is configurable value. Beyond that, there is no meaning in keeping the files which are not at all contributing in our actual data. So how to delete those also we'll be inspecting in our upcoming session. Till then, stay tuned, try to practice parallelly along with this notebook. You'll be getting a better idea out of it. And if you have any doubt in any stage of this video, just ask in the comment section with a timestamp. I'll be surely trying to revert back ASAP. Stay tuned. So we'll come back to our next session where we are going to explore some more concepts related to Delta Table. And especially in this particular section, we will be focusing on different ways how we can read and write data in DeltaLake using Spark. So already in our previous section, we have focused mostly on SQL based approach. And apart from that, I have also covered how we can read data from DeltaLake, right? That is using spark.read.format. And in the format, you have to mention this is a delta format. That is delta file you want to read in this particular Spark data frame. To define that, we have to use this part, okay? And if you want to read any specific version from history, you have to use option version as of and provide the version number. And if you don't want to read some specific history, just want to read the latest version, you no need to give this option version as of parameter. And then you have to provide the S3 path where your Delta Lake is sitting. That way we can read the data in a Spark data frame from a Delta Lake. Now let's try to explore another very simple approach. I'll just zoom this little bit, and that is using spark.table, as simple as that. So already we have created this particular delta table in our blue data catalog, right, in our previous video. That let me just show you. I'll go to data catalog and then database, and then here you'll be seeing there are two databases. One is default database, and this is the database what we have specifically created for Delta Lake experimentation purpose. There we have already created this delta table, right? So suppose you want to read the delta table data, instead of reading in some other way, you just can simply use spark.table, and that way from the glue data catalog itself you can read the delta lake table. So let me just quickly show you that. So before that, to start the notebook, I will execute this particular command. This is very vital, and now I can execute that command. So this one, and if I just execute if product read.show, here obviously because this cell we are running for the first time post our notebook start, so it is going to take few seconds. But once this Spark session is created, you will be able to see that it is showing the same data whatever in current Delta Lake version we are having. So here it is, you can see waiting for session to be created. So let it get created, and then if you execute this command, that is in this data frame, what are the class name and input file names available, and out of that if you want to get the distinct data, you will able to see that this particular code will give the same output what we have received earlier while reading the Delta Lake data as spark.read.format delta. That is the same code when we have executed here. If you observe here, if you see, earlier we have already executed this, right? That is spark.read.format delta. So there we were getting this data frame as output. ID 𝒄𝒆𝒄 testing update, another category 𝐼𝐷𝑆 and testing update, and 3 distinct input file name. Same thing you will be getting. There is no difference in the output if you read the file in this way. Okay. So here you can see this session is created, and this is the data what it is showing. And now if I execute df product read and select, so here it is showing input file name is not defined. Okay, right. So I have to execute one command because I just now started the notebook. So the PySpark input command is not there. So I need to execute that. So instead of this line, I will be writing from PySpark.scale functions input start. Okay. And now if I execute this command, here you will be able to see again 4 distinct class and 3 distinct unique file names. Here you can see that is 4 distinct class and here 3 distinct input file. Totally there is 5 unique combination with respect to class name and input file. That we are getting same result as earlier. Now another way to read the delta table in a Spark data frame is this way. Okay, so what we are doing here, if you observe this particular markdown, that use the delta table path instead of the table name in the query, and this directly reads the data from the path without checking the table statistics. That is, whenever I want to execute select star from a particular table and then I am using spark.sql to create the data frame, that time we need to mention the exact table name whatever we have created in glue data catalog. But in delta table, there is a feature that you can directly refer the S3 path instead of going via glue data catalog, and that is this manner. Select star from, you have to use delta dot, this is compulsory, and then here you have to mention the complete S3 path where actually your delta lake is available. And if you see here, our delta lake is available here. If I go to properties, if I do a command F, you will be seeing that same S3 URL I am using, right? So this is another way to read delta lake data in a Spark data frame. So we have explored 3 ways. So maybe here I can do dfpath.show, and here you will be able to see the same data. Okay, so 3 ways we have explored. One is using delta dot and S3 file name. One is directly using the glue data catalog, that is database name dot table name. Another way is spark.read.format data, right? So these are the major ways which is used in industry to create a Spark data frame from a delta lake files. Okay, right? Now obviously you can apply all generic transformations as we did earlier in this approach also, like class name, input file name. If you want to get the distinct counts, you can get that is not a problem, right? So now reading operation is fine. Now the next concept can be how from a Spark data frame we can write the data back to some delta lake. That we need to understand. So for that, this is the command. Okay, so here writing data in delta lake. So the command is pretty much similar. If you find, just instead of how we generally write df.write.format Parquet, now we have to use df.write.format delta, and then mode, override, append. These are default modes in PySpark as we know. And then option. In option, we need to mention the path, that is in which external S3 location or in which data lake folder we want to create our delta lake. That path we have to mention. Okay, and I have mentioned here a completely different S3 path. Okay, that is iris data delta 2. So actually, if you see in our earlier discussion, we have created the delta lake here. Now I want to show you the data write operation as a delta lake data. So to understand the concept in a better way and whether Spark is properly writing the delta lake data or not, I am just creating another folder where our delta lake will be created. Okay, right? So that is the path we have to mention, and then save as table. So this is how generally we write the PySpark data frame in some external stage as well as in glue data catalog, right? Suppose for example your requirement is not only writing the data in a S3 location, that is in data lake or delta lake, whatever you say, but also you have to create a glue data catalog table so that the data analyst team can query using that particular table, right? So for that time we generally use save as table. So that same concept I am using, just the new change is format delta. And when I will execute this particular thing, 2 things will happen in the backend. Number 1, there will be a new folder will be getting created, iris data delta 2, within which the data will be written in Parquet file format. Along with that, all the transactional logs will also be created as _delta_log folder, how we have seen earlier. And not only that, one more table also will be created in our glue data catalog. As of now, you can see here we are having only 2 tables, CSV table and delta table, right? But now in this write operation, I am creating another table with the name delta table 2. So that also we need to observe. So here you can see we are writing the data. So it is going to take some time. So here you can see the code is executing and it is done. So if I go back to my S3 data lake and if I refresh, here you will be able to see that that particular folder with _2 should be created. And here you go, iris data delta 2. Within that, if we go, same how we observed earlier, that data as well as transactional logs are stored. So this is the Parquet file where Spark has written the data. And if you go inside delta log, here you will be able to see that one JSON file is created. I can download and show you, not a problem. And here if I open this one, here you will be able to see that it is an additional activity. Okay, and this particular Parquet file is added. Obviously, it has given the metadata informations also for our table structures, and the main operation what Spark is doing is create or replace table as secret, right? Why create or replace table? Because here if you observe in the Spark notebook, we are overwriting the data. That's why it is create or replace, right? I hope you are getting this. And also if I go to my database and refresh, here one more table should be created. And let's see, that is if you observe delta table. Okay, right? So this is the new table created due to our Spark write operation. And in this particular table, if you go to advanced properties, you will able to see the path where this particular table is pointing to. It is pointing to IDs data delta 2. That is this particular new folder whatever is created, IDs data delta 2, right? So up to this, it is totally making sense. I hope it is clear to you. Now obviously you can perform all the transformation and again write the data, that is also fine. For example, df3 equal to df2 dot filter, and I want to take only the class name which is belonging to 𝐷 and 𝐷. That also is perfectly fine. And if I execute df3 dot show, here you will be able to see earlier this data frame was having multiple classes, but now this time it is having only id status and id structure. And then again I can write this data in our delta lake. So because already table is created, I no need to again execute save as table, but rather I can simply use save and again format delta we have to use. And suppose we want to overwrite the data, so that time I need to execute mode overwrite. Okay, right? So I will run this one, and here you should be able to see that one more Parquet file will be created, and this particular Parquet file will be deregistered because we are overwriting the data. So that means this particular older data will no longer be needed, although it will be there in our data lake for some time until and unless that default time limit it is exceeding, and delta lake will automatically delete that. But that will happen later. Immediately obviously it will not happen, because as I told you that default time for unused file deletion is 7 days. So anyway, this file will be there, but one more new file will be created. Here if I refresh my delta lake, here you can see that at 2056 one new Parquet file is written, and in the delta log it will be showing that this new file will be addition and this old file will be removal. Okay, because this old file no longer needed for our delta lake. So that I will show you. So here you can see one more transactional log is created for this delta location. I can download this one, and here if I open, maybe as I told you, right, that this is the old file based on timestamp, I can understand. So here in our transactional log, if I do a command def, and here you can see this particular file is removed, and this new file, right, this one which is having greater timestamp, that should be added. Here you can see it is an additional activity, right? So this is how from PySpark data frame you can write the data in delta lake. So in this particular section we have explored majorly how to read and write delta lake files using Spark data frame. So this is all for this particular section. We will catch up in our next section. Till then, try to do the same lab section based on the notebook, whatever I will be providing in the description box. And if your lab is getting completed, then don't forget to stop the notebook post save operation. Okay, because if you are not stopping it, unnecessarily it might incur a huge cost. Okay, so always try to save the notebook and stop the notebook to save your AWS cost, right? We'll catch up in our next section. Welcome back to another new session in our Delta Lake course. And today in this particular video, we are going to explore the Delta Lake library. So in our previous videos, we already have covered several concepts around Delta Lake, how to create Delta Lake table using SQL, how to perform insert, update, delete, and how Delta Lake track all those transactions using Delta log transaction files, which is in JSON format. And then we have also covered how to read the Delta Lake data in a Spark data frame and write the data back to a Delta Lake using PySpark. That is this kind of command we have already executed. If you just have a quick recall, like here already in the upper section, spark.read.format delta. This way we can read the delta formatted file, and to write the data we have explored this command, that is df.write.format delta, and then you can use either mode equal to overwrite or mode equal to append, which are default format of data write pattern provided by Spark. Now if you consider this delta write operation using PySpark, we are having two things. One is overwrite, one is append. That means either the complete data will be overwritten or the complete data frame data whatever we are having in our PySpark, that will be appended. But the essence of DeltaLake is basically in inserting, deleting or updating few rows or few records in our DeltaLake. So directly using PySpark write operation, we cannot achieve that because it is impacting the whole location, either completely appending the data, and obviously delete operation is not something what we can append, right? Only insert operation related data points can be appended. So using simple append operation, we cannot perform insert, update, delete everything. And if you consider overwrite, it is just simply overwriting the whole data. Now if your table is having very big volume, then obviously this overwrite will be a very expensive operation. So we need some sort of mechanism using which we can update or insert certain rows from our Spark data frame. And when we discuss these kind of operations, then obviously the concept what comes in our mind is merge operation. Like if you consider in default SQL, we are having merge operation, right? That is, if in target table there is no data existing, but in source table it is there, then we should insert. But if in target table it is existing and in source tables also it is existing, then we need to update the data in target table. When matched, then update, or when not matched, then insert. Those kind of operation if we want to do, that time the simple Spark df read operations might not help us. And that's where DeltaLake library comes into picture, which helps us in performing selective update operation like how we do in merge statement using our Spark data frame. Okay, so obviously you can explore more about this from this DeltaSpark module or package. So in this particular video, we are going to understand the basics of this DeltaSpark module, how to work with this, and in our next section, we will be exploring how we can perform merge operation using this particular module and Spark data frame. So as a first step, what I'll be doing, I'll be executing this default cell, that is configuration, DeltaSpark session extension and data lake format as delta, and then I will again go back to my cell where I supposed to read the data using DeltaSpark, and that is this one, read data from delta table via DeltaLake library. So as a first step, we need to import this module from delta.tables import start. Now using this delta.tables, you can basically perform various operations in your DeltaLake. Obviously one thing is with this Spark data frame, you can perform several computation like merge statement, etc. And even you can use this one to do simple insert, update, delete operation as well. So that also I'll be showing you. So first, that is query a DeltaLake table using this DeltaSpark module. So for that we are having this kind of command. That is, first we need to create a delta table data frame equal to delta table dot for name, and then you have to pass this Spark session and then the database name dot table name. Whatever delta table name we have given in our meta store, how we have created that name we can pass. So that way this particular delta data frame will be created. So I can run this one. So obviously it is going to take some time because the first cell is still running, because this is the first cell, so session is getting created and post session creation this import will happen. So that's why it is going to take some time, and then you can see our this cell is getting executed. This is going to read our delta table data from blue meta store. Okay, so this delta table already we have created pointing to our initial delta location, that is ID's data delta, where we are having 7 files, right? So here you can see this particular cell execution is complete. Now if I do delta table.show, here you will able to see it is having no attribute.show. So try to understand, this is a delta data frame, not a default Spark data frame, right? So .show operation will not work. So rather than that, we have to use .2df and then we can use .show. So that way first from delta table it will be converting to a Spark data frame, and then we can perform show operation on top of it. Okay, right? So here you can see it is getting executed and it is going to show us the data. Okay, even you can perform all sort of operation, like suppose first I am converting to Spark data frame and then I am selecting the class name and whatever distinct class names are available that I want to consume. Okay, so if you recall in our initial discussion, we are having totally 4 class names. ID is 𝑑 is 𝑑, another class, and there is testing update we have also created, right? So I'll be running that one. So here you can see that same 4 classes are available, how we have observed earlier from our initial Delta Lake. Now this approach we have explored, that how we can create data frame using DeltaSpark module, but we are reading the data from Metastore. Now you can also read the data from S3 Data Lake directly. So that time instead of for name, you have to use for path. Earlier we were using for name right here, but this time we have to use for path if we want to read the delta data frame from S3 location directly. And then you can execute all sort of operation after converting to Spark data frame if needed. Okay, right? So this is basically another way how you can interact with delta table. That's all I am trying to show you as of now using DeltaSpark module. Then you can perform delete operation using DeltaSpark module. This is the code, that is delta table dot delete, and I want to delete all those rows where id equal to 100. So here you can see, before executing that code, let me show you that if I sort based on last modified, here the last timestamp you are able to see 9:23 p.m. on 28th January, and today is 30 January 8:39 p.m. right? So I'll be executing this particular command and let's see how it works. So here execution is complete. So maybe one more new file will be created which will have the rows deleted for which id equal to 100, and here you can see one new Parquet file is created, and based on that obviously our transactional logs also will be updated. Like here you can see last transactional log was on 28 January, but now one more is created. So this is basically a delete operation, right? Now similarly using DeltaSpark module, if you want you can update something. For example, delta table 2.update, and here I can basically execute the update command using condition. So it is just like where clause how we put in update query, that is for id equal to 119 set the petal length as 1000. So before executing this cell, let me show you what is the actual value. So maybe here I can convert this to a Spark data frame and then dot, maybe I can apply filter and then here delta table 2 of id equal to 190. Okay, and then dot show truncate equal to false. Let's comment this part. So just we are converting to a Spark data frame and I am applying a filter clause to view the current data. Delta table object is not subscriptable. Okay, so sorry, here I have used delta table 2. So this kind of operation we cannot apply on DeltaSpark data frame. So maybe here I can give df5 equal to and then here df5 equal. Okay, so first from the delta table I am converting to a Spark data frame and then I am executing this. So filter expected 2 argument but 1 given. Sorry, df5 dot filter. So here you can see currently in our delta table whatever id 199 is there, for that the petal length value is 1.5. But suppose using DeltaSpark I want to update. So this is the simple update command, that first we have to give where clause condition and then set the column name we can set within the dictionary, whatever values you want to update you can. So let me execute that, and here it is getting executed. So that this step is done, I'll be replicating this cell in a new tab, and now what I will do, I will basically copy this command and then paste that here. And now if I execute df5 show, that is from our delta table, here you can see petal length is converted to 1000. Earlier petal length was 1.5 but now it is 1000, right? So basically whatever activity we have done using SQL query now, that is selective insert, update, delete operations, those all operations you can perform using DeltaSpark module. Okay, but the best beauty whatever is available for this DeltaSpark module is in merge operation. That is, suppose already we are having this Delta Lake data stored in S3 or some other cloud storage, and I got another Spark data frame. Now I no need to overwrite the complete Spark data frame here, nor I need to append the complete Spark data frame here. I want to selectively insert or update whatever rows are available in that Spark data frame as well as in our Delta Lake. In those common rows, what I want to do, I want to update the Delta Lake data with the Spark data frame data. And whatever rows are available in this Spark data frame but not available in Delta Lake, those alone I simply want to insert. That kind of selective operation we can perform using merge statement. That we are going to explore in our next section. So as of now in this particular section, we have explored how to interact with DeltaLake using DeltaSpark module. Whatever operation we have done till now using insert, update, delete command using basic SQL, using DeltaSpark, we are able to do those insert, update or delete in Python programmatic way as well. So try to perform this particular experiment. You will be getting better hands-on idea out of this. Stay tuned for our next section. Welcome back to another section in our DeltaLake learning journey. And today in this particular section, we are basically going to explore how we can execute, update or insert this kind of activity in our S3 DeltaLake using Spark DataFrame. Okay. So obviously as a first cell, as we generally do, we need to execute this particular cell, which is basically configuring all the required stuffs to work with Delta and AWS Glue notebook, right? And then in our first section, we have explored how to perform insert, update, delete in DeltaLake using simple SQL query. And it is obviously like how we generally work with data warehouse or database system, like using simple delete command, we can perform some delete activity. Using simple insert command, we can perform some insert activity in our DeltaLake, right? And even using update command, we can update some data points in our DeltaLake using simple SQL. Then eventually we move to Python based approach, and there the DeltaSpark module we have utilized in our previous video, right? So if you just recall, so we had to import this particular module from delta.tables import star, and we have created a delta table data frame pointing to our DeltaLake that we can do in two ways, either using Glue data catalog if already a table is created on top of that DeltaLake, or you can directly read the data in DeltaSpark module using S3 path as well. Like here we have explored delta table.for path, and then we have observed how we can perform insert, update, delete using DeltaSpark module. So earlier we have explored using SQL based approach. Now this is Python based approach. So here basically in our previous video we have explored how we can change, that can be delete, insert or update etc. as a single row element. For example, ID 100 we want to delete, right? Or maybe some data we want to update, that time we need to execute this kind of update clause. But these are impacting one or few rows at a time. But suppose if you are considering big data environment where we generally use Spark to process huge volume of data, that time how to perform insert, update, that concept we are going to explore in this particular video. And obviously that time I hope you are getting this, that the merge concept comes into picture. So if you are already aware of merge statement in SQL, that same concept we are going to utilize here. So if you just recall, the general command for SQL merge statement looks like this, that is merge into target table using some sort of source table on, and then we provide some column names both from target as well as source, kind of a join clause you can consider. And then when matched, that means when there is matching key between source and target, then maybe we want to update some rows in the target table. So update say target table dot column 1 equal to value 1, and this value 1 generally comes from the source table, right? And when not matched, then insert. That means when in target table there is no such ID which is available in source, that means that particular row is a new element in the source, right? So obviously we need to do insert operation that time. So DeltaSpark module basically helps us in performing merge operation in a very big volume of data. For example, you are already having DeltaLake and that huge volume of data is already available, and you are having another Spark data frame which is having data maybe from some OLTP database, and then you want to update huge number of rows in DeltaLake, or maybe insert huge amount of rows in DeltaLake from that Spark data frame which is coming from our OLTP system, right? So that time this kind of single delta table.update or delta table.delete, this kind of operation become very complex, right? Because one row we cannot simply apply this kind of filter and delete or update or insert these rows. So that time delta table is having the functionality to execute merge statement, and how that we are going to observe. So as a first step, what I am going to do, I am going to create a fresh DeltaLake. Okay, so here I am having some dummy data, and I am writing this particular data as delta format in this particular S3 path. ID is data delta 3. So if you observe, as of now in our DeltaLake, we are having only these two folders belonging to DeltaLake. ID is data delta and ID is data delta 2. ID's data was having actually CSV data, that was not a DeltaLake. So here what I will do, I will execute this particular command. So let's see. So it is going to create the session because this is the first cell, so it is going to take some time. So let's wait for that. just a simple write operation we are doing from Spark data frame, how we generally write in Delta Lake. That particular pattern I am following here. Okay. So session has been created. Now I think write operation also should be completing soon. Maybe we can go back to our Delta Lake and refresh. So here till now the folder is not created. So for some time. So here this particular cell execution is done. If I go back to my Delta Lake and refresh, here you will see that this is the folder creation command and here is our actual folder. Within that, to store the actual data in Parquet file format, these all files are getting created and our delta log is also created for this particular transaction, because when we are doing spark.write.format delta mode override, so this is nothing but going to write some data. So again one transaction, right? So here maybe I can download this data and show you. So here you can observe. So here one file is added, another file is added. This is second one, this is third one, this is fourth one, and this is fifth one, and here it is sixth one. So 6 Parquet files are basically added, right? Now if I go to my Delta Lake and count the Parquet files, 1, 2, 3, 4, 5, 6. So 6 Parquet files are written by our Spark data frame, right? So up to this I hope it is pretty much simple. Now as part of our next section, what we are doing here, I have written df.show also, if you observe. That's why it is returning the data frame. Now suppose there is some update operation going to happen, okay, and maybe this incremental data came from some OLTP system, maybe some RDS, etc. What it is saying that product ID 1, here if you see in our earlier data frame also product ID 1 was available, and this data is already stored in Delta Lake. That means it is past data. But in today's record, product ID 1 also came. Price got increased. Earlier price was 250, but now it is 400. Okay, and rest columns are pretty much same. And if you observe the second element, product ID 7, here if you observe in our Delta Lake, product ID 7 itself is not available. So it is a new record. So this particular row from Spark data frame we need to insert, and this particular row from our Spark data frame we need to update in Delta Lake, right? So like this way, suppose we are having huge volume of data. Now one by one you cannot simply perform update or insert operation. So there comes our Delta Lake feature of merge statement. So what we need to do? First we need to create a Delta data frame, not Spark data frame, pointing to our current Delta Lake. So here if you see Delta Lake table 3. So why I have given the name table 3? Because here if you observe, when we have written the data in this new Delta Lake, here we have created the entry in blue data catalog also, that is this table need to be used Delta table 3. Okay, so pointing to that particular metadata location, here I have created a Delta data frame. And if I want to view the data, so obviously I need to convert that to a Spark data frame and then only view the data. So name Delta table is not different. So first we need to import the Delta table module, which we have done in our previous section from delta.tables import star. So once that is done, we are good to execute this command as well. So here let's execute that. Okay, so here you can see the execution is going on, and here it is done. It is going to show the same data whatever we have inserted basically here, right? So here if you see the product ID 1 price was 250, right? Even here also product ID 1 price is 250. Obviously it is not going to be changed because we have just written the data and read in Delta data frame. Okay, now with respect to our Spark data frame, we want to execute merge statement. So first our target is Delta Lake. So Delta data frame I am considering as target. You can find lot of similarity with SQL merge statement. That's why I have written here. So merge into target table. So here in Spark, if you write first target table is Delta table here or our Delta Lake. That one we are giving an alias name as products. And here we are using dot merge, like how in Spark you use df1 dot join df2. So merge is also kind of a join operation. So same syntax dot merge. And then here the second data frame we are taking our Spark data frame. This is not a Delta data frame. Okay, so df product updates. If you see df product updates is having updated or new rows to be inserted, that data we are having. So that we are giving the name alias name as updates. Now the next step here, if you see in SQL query, we need to provide the merge condition, kind of a join column. So here we are giving that. So from target table product ID, that we have to match with source table product ID. And if they are matched, that means in target table also one entry is there, in source table also one entry is there. So obviously we need to update the target table, that particular row, with current source table data. So that one only we are doing. So here product name product name, this particular thing when you are writing, that means this is belonging to target table or our actual delta table current state, or table name with alias products. So that particular product name in our target we are updating from source table product name. Okay, so in our source table also the product name is available. If you see here, this particular cell, let me execute. So this is our source, and here product ID is available, obviously that is needed for join, and all the columns in our delta table we are basically updating, as simple as that. Price also updating, category also updating, and update at timestamp also we are updating from source whatever we are getting. That means in target table we are updating the complete row, all the columns with our source table data current state. Okay, and when not matched, that means if there is some ID which is available in source but not available in target, that time only it will not having any match. That time we are simply inserting the data. So when not matched, then insert, or when matched, then this is the simple command. And how we use in Spark dot operation is dot operation, we have to write the code, and then we have to use dot execute command to execute this merge statement. So let me execute this particular merge statement, and as a result what will happen, that this particular row will be updated and one new row will be inserted with entity product ID 7. Okay, because this is not there in our target. So here you can see it is executed. Now if I do delta table.uf.show to view our current delta table data, here you will be able to see that product ID 7 is added, and for product ID 1, where earlier the price was 250 rupees, now it is getting updated to 400. Okay, so this merge statement basically helping us in updating or inserting huge volume of data from Spark DataFrame to our Delta Lake, and that's the main advantage of using DeltaSpark module while working with Delta Lake. And if you go back to our Delta Lake, here obviously you will be able to see some new files will be written, and here if you observe, say just sort based on last modified time, earlier files were written at 12:40 PM, but this is a new file which is written at 12:48 PM. Maybe I can download this particular data and open in a Parquet viewer to show you how it is looking. So here if you see only the inserted data, that is product ID 7, and the updated data product ID 1 is available. Okay, why we are not having other rows which were earlier existing? Because those are available in different Parquet files which is not even touched. Maybe in our earlier case we were having one particular Parquet file where the product ID 1 was available. Okay, so that particular Parquet table alone the Delta Lake has removed, and it has appended or added this particular new Parquet file where both product ID 1, that is update row, and product ID 7, that is insert row is available. That way intelligently it is working. It is not impacting other Parquet files. So obviously if you go to Delta Logs, here you will be able to see our second transaction. If you download that, the Parquet file related to product ID 1, that has to be removed, and this new Parquet file should be inserted. So one add, one remove. So here if you see one remove happened. So this Parquet file, for sure this Parquet file was having the product ID 1. Let me download and show you that also for your easy understanding. So this is the Parquet file. Let's download. And it was earlier written, so I am hoping that this should have only data related to product ID 1. That's why that alone is deleted. So here if you see, we are only having product ID 1 in this particular, and that alone is deleted or removed from our Delta Lake. It will no longer contribute in our Delta Lake data, and this new Parquet file is available which is having product ID 1 and product ID 7. Just now I show you, right, the data which was written at 12:48 PM. So this is how merge statement is working, and this is a very powerful concept to insert or update huge volume of data at a single go. So with this, I hope the concept of DeltaSpark is clear to you. Try to perform this particular experiment. If you are having hands-on, you will be getting this particular concept in a much better. So this is all for our this section. We'll be continuing in our next section. Till then, save this particular notebook and stop the notebook to avoid unnecessary cost. Thank you. Hello friends, welcome back to our next section in Delta Lake course, and in this particular section we are going to explore some optimization techniques what we can apply in Delta Lake tables. Okay, so first optimization technique what we are going to explore is related to resolving small file issue. So for this particular optimization, let's first create a Delta Lake. So here if you see, I am importing from PySpark.sql import row, import time, and here I am creating some dummy data. and out of that I am creating a Spark data frame, and I am writing the data in delta format in our DeltaSpark testing bucket within ID's data delta 4 folder. So if you recall, in our previous video we have created 3 delta lake, right? One is ID's data delta, one is ID's data delta 2, and one is ID's data delta 3. Now we are going to create one more delta lake in the folder ID's data delta 4. Okay, and pointing to this particular folder location, we are going to create one table also, which will be available in glue data catalog, and that is DeltaLake db.delta table 4. As simple as that. So if I just open my glue data catalog in a new tab, here DeltaLake db is already available, which we have created, and these are the 4 existing tables. There is no table with the name delta table 4, right? So now what we will do, we will quickly run this particular step, but before that we need to make sure we have ran our first cell, which is basically configuring the required modules and packages for DeltaLake to be used in this glue notebook. So this cell we have executed, and then I will be going back to my original cell, and here I can execute this one. So here if you observe, it is waiting for this Spark session to be created, because this is the first cell, so it is going to create this Spark session first, and then only it will be executing all the required codes. Okay, so let's wait for some time. So now the session is created successfully. Soon this Spark data frame will be created, and due to this df product.show operation, the data frame also should be visible here before writing the data in DeltaLake. So here now the data frame is visible, so we can hope our write operation is also successful. If we go to our bucket and refresh, here you can see that ID's data delta 4 folder placeholder is created, and here data is also written in this folder. So we are having Parquet files where actual data is stored, and within _delta_log within this particular folder, the transactional information will be stored, right? So this is the first transaction what we are doing in this particular DeltaLake. So if I just download this JSON content, you will be able to see that it will be having the information that 1, 2, 3, 4, 5, 6 Parquet files are inserted in DeltaLake, something like that. So here you can see one add activity, second add activity, third add activity, fourth add activity, fifth add activity, and sixth add activity. Total 6 Parquet files are added in our DeltaLake, right? So maybe let's download any particular file and let's see the content. So here Parquet file I will be downloading, and Parquet file we cannot directly view. So to view that, I am using online Parquet viewer. So here I'll be opening that one, and here you can see the Parquet file content. So it is having product ID 1, product name, heater, price 250, category electronics, and this. So one particular Parquet file is having only one row related to product ID 1 from our this particular data frame, right? So obviously I hope you are getting this, that this is having a small file problem, because one file is having only volume 1.5 KB, and suppose you are having a huge volume of data like this in your DeltaLake, then obviously read-write operation will be very much expensive. On this I have already discussed in detail in one of my previous video. The link I'll be providing in the description box, and that is related to small file issue and how to resolve that in DeltaLake system. So in DeltaLake also that particular issue now we are encountering. So now what solution we can implement, let us try to understand. So to resolve this small file problem, DeltaLake provides us one optimization technique using which we can group certain small files and create little bigger files which will be optimized for read-write operations. Okay, so that how to do, let us try to understand. So first what we are going to do, we are going to import delta tables, and pointing to our DeltaLake location, we are going to create a delta data frame. This is not a Spark data frame. This particular data frame is delta data frame, which is created using DeltaSpark module, which we have already encountered in our previous 2 sections, right? We need to pass this Spark session and the S3 path pointing to our DeltaLake location. So here we have written the data in this ID's data delta 4 folder. Pointing to that same location, we are going to create our delta data frame. Okay, and now to optimize the file size, that is to compact all these small files and make a bigger files, to do that operation in DeltaLake, this is the command. If you are having a delta data frame, there you can apply this particular method dot optimize, and then execute compaction. So this particular line of code will take your small files, apply compaction and create a bigger file. Okay. Now with respect to transactional operation, what should happen in the backend? That all these small files should be deleted, or kind of remove operations should happen for all these small files from our Delta Lake, and one new bigger file should be added in that Delta Lake, right? So that we will observe. So just I need to execute this delta data frame dot optimize dot execute compaction, and it is going to basically execute the small file optimization, and some kind of output it has written in the console also. This one you can explore yourself. I want to show you specifically what is happening in our Delta Lake. So here if I refresh and sort based on last modified, here you will see that for all the earlier Parquet files, it was having the last modified timestamp 1756, that is 5:56 p.m. But one particular Parquet file will be having higher timestamp, which is just now written. Currently it is 6:02 p.m. and if you observe this file, 6 p.m. 1 minute 50 second. So this is the new file which is written by our Delta Lake optimization. And maybe we can download this particular file and inspect in Parquet viewer what is going to happen. So I'll refresh this and I'll upload our new file. And here you will be able to see the complete data frame data, whatever we have inserted in our new Delta Lake, that is available here, right? Those all small files it has combined and created this bigger chunk. So now all the earlier small files is no longer needed, because this single Parquet file is having that same information. So ideally that should also have been tracked in our Delta log. So here if I go to my Delta log transactions, here you will be able to see that one more new transaction is created. And if I download and open this particular file, here you will be able to see remove. That is 6 Parquet files are removed. Whatever earlier Parquet files was inserted in our earlier operation, all those are removed and one new Parquet file is added. And this Parquet file is obviously the same Parquet file what just now I have shown you. So if I just do a search, here you will be able to see this is the Parquet file which is having the timestamp 6 p.m. 1 minute, right? So this is how optimization is happening in the backend, basically kind of helping in resolving small file issue. It is just simply taking all these small files and making a larger files. Even if you don't want to execute using DeltaSpark data frame, but you want to use native SQL, that time you can simply use this SQL query as well, that is optimize and then delta.s3 path. How I have already shown you, right, that any Delta Lake data you can read in SQL like this way as well, that is delta dot and then your complete S3 path where your Delta Lake is available, and there you can put optimize command to perform compaction. Okay, but now if I execute, it will have no result because already compaction is done. So with respect to our Delta Lake, no more compaction is possible as of now. So that's why no transaction will happen. So here maybe if we refresh, and here you will be able to see that earlier file is only available and no new transactions will be created. If I refresh my transaction location also, no new transaction is created because already we have executed optimization in our this particular Delta Lake location using Python command, right? So that's what I have written here. If you run optimize twice on the same data set, the second run will have no effect. This is also known as idempotent operation. Basically same thing what we observe while performing other idempotent operation, right? So even if I execute second time, here you will be able to see nothing, right? And what this optimize operation basically doing, it is merging smaller files into bigger ones to enhance the storage efficiency and performance. This means that if you read the data before and after optimization, you will get the same result. And this is obvious. Optimization is not changing the actual data content. It is not deleting or inserting some new rows. It is just performing some optimization with respect to storage. So that also I can show you. Maybe I can give a plus and df equal to spark dot read dot format delta and then dot load, and here I can pass this particular S3 path, and then here df dot show if I perform. Here you will be able to see that same data whatever we have inserted in this particular location, right? So optimize operation is not going to change the data. All it is going to do is resolve your small file problem. Okay. And now let us try to understand a little bit in the backend how it is working, right? So on that I have written here that optimize is a delta utility function that comes with two variants. One is Z order or Z order and another one is bin packing. The default one is bin packing. What is Z order or Z order optimization? On that I am going to cover in my next section. So let us try to understand this default operation bin packing, how it works. And it is a very simple thing. What exactly is bin packing? At a high level, this is a technique that is used to coalesce many small files into fewer large files across an arbitrary number of bins. A bin is defined as a file of maximum file size. Default one is 1 GB, right? So it is nothing. You can consider there is some 1 GB locations is available, which is basically our larger possible file size. There it is going to put all these small files or combine all these small files as long as combiningly the small file is having volume lesser than 1 GB. Once it exceeds 1 GB, it is going to have another bin or another large file where the smaller files will be combined. As simple as that, right? So in our this particular Delta Lake, what happened? After combining all these small Parquet files, the larger Parquet file is having only 1.7 KB, right? That's why only one large file is created. Suppose after combination, one particular large file is exceeding 1 GB, another big Parquet file will be created. Like that way, bin packing will work basically in the backend. Okay, right? I hope you are getting this. And now obviously you can play with history command to inspect how the optimization is working in the backend. So already in our previous video, I have explained you that using history command, basically you can check all the operations, whatever happened in your Delta Lake, right? So let me pull out that particular command once more. So this is the command view history, and here I'll be going below, and here I'll be clicking a plus icon, and here our delta table. In this particular video, what we are using is delta table 4. So that one I'll be using. So let us try to understand what are the operation or transaction done on delta table 4. Okay. So here if I execute this particular cell, here you will be able to see two operations. In the version 0 or first time, what we have done, we have executed create or replace table as select. So that means table creation as well as inserting data operation, that one we have done. In the second operation or in the second transaction in the version 1, we have executed optimization command. So in the operation tab, here in the operation column, you will be able to see it is written optimize. That means optimize command is executed, and due to which 6 files are removed and added file is 1. That's what we have observed, right? So here if you see 1, 2, 3, 4, 5, 6, all 6 Parquet files what are having last modified as 1756, those all were removed and only one new Parquet file is added. So this particular optimize command, how many files it is removing, how many files it is adding, if you want to observe separately instead of SQL query, you can execute this kind of command also. You can take help of DeltaSpark module to get the historical information like this way. So here I am importing call from PySpark.sql.functions, and here first I am creating the DeltaSpark module from our glue data catalog, that is DeltaLake db.deltatable 4, and using .history command you can inspect the operations done in our Delta Lake. Okay, so earlier using SQL if you want to do, you can do in this way, or if you want to do using DeltaSpark module, you can do in this way. So DeltaSpark module not only support insert, update, delete operation or merge operation, but it also helps in historical transaction tracking, etc. also. Okay, and here I am filtering that where column operation is optimized, and from there I am going to extract these specific columns. Okay, and truncate false I am applying. So if you observe, we are having a column called operation matrix in the history, where these all informations are available, like how many files are removed, how many files are added, so on and so forth. So it is kind of a map data type or structured data type, we can say in Spark. So to extract the fields from map or structured data type, how we use, that is column name and then dot field name, that approach we have used. So if I run this particular cell, here you will able to see that in version 1, the optimize command was executed. Using this filter command, we are getting this. This is the time when it was executed. Operation is optimize, obviously. And how many files removed? That is 6. How many files added? That is 1. Right? So this is one way to view the optimize command operations, whatever we have executed in our DeltaLake. Right? I hope you got this. So in our this particular section, basically we have observed bin packing optimization to resolve this small file issue in our DeltaLake. This is all for our this section. We will catch up in our next section. Stay tuned. Welcome back to another new section in our DeltaLake journey, and today we are going to explore Z order or Z order optimization. Okay, so already in our previous section we started discussion on different optimization techniques what we can implement in DeltaLake, and we have already discussed bin packing optimization, right? That optimize command can resolve this small file issue and create larger files using another technique, and that is Z order or Z order. On this we are going to explore in detail in this particular section. But before jumping into the core concept of Z order optimization, you should be having a clear idea on predicate pushdown, what I have already discussed in one of my previous video. The prerequisite link I'll be providing in the description box. Because Z order optimization is having kind of more similarity with respect to the concept of predicate pushdown, using which Spark basically skips some files while reading the data. For example, just a quick recap. Suppose we are having file 1, file 2, file 3 in our data lake, and if you consider the file formats generally in data lake preferred is Parquet, _, etc. So that way it will be compressed and will be taking lesser space. And generally with these Parquet files, we are having statistics associated with the files. Like here, if you observe a column is having value 1, 2, 3. Now in the statistics section for the Parquet file, it will be written minimum value is 1 and maximum value is 3. Whatever is available for this column in this file 1. Then similarly for file 2, if it is having 4, 5, 6 these IDs, then mean value is 4 and max value is 6. This information will be stored as statistics in the Parquet file. Same goes for file 3. If it is having 7, 8, 9 IDs, then mean value 7 and max value 9 will be stored as statistical information. Now if you are executing a query, select star from table 1 where column value equal to 9, then it no need to read all the files together. It will just read the statistical information and it will try to find out where this column 1 equal to 9, this value can possibly be available. For example, if minimum value is 1 and maximum value is 3, and if I am searching column equal to 9, that means obviously this particular row will be not available in file 1. So file 1 it will be skipping while performing data scan. And following that same manner, if the mean value is 4 and maximum value is 6, it is not possible that the column 1 equal to 9 value will be available in this file 2. So obviously in file 3 it will be scanning, because for file 3 the minimum value is 7 and maximum value is 9, and we are looking for value equal to 9. So that means this particular row will be available in file 3. So that way in the scanning operation, file 1 and file 2, it is not at all checking directly, it is scanning file 3. So that is basically fundamental concept of data skipping using predicate pushdown. Now Z order or Z order optimization basically take help of these kind of statistics in data skipping in DeltaLake. So how it works, that let me explain. So suppose in our DeltaLake we are having 4 files, file 1, file 2, file 3, file 4. All are obviously Parquet files, because as we already know that in DeltaLake the actual data is stored as Parquet file format, whereas all the transactional logs get stored as JSON file format, right? So because we are considering the raw data now, so obviously these are Parquet files. So for these Parquet files, the minimum and maximum values are generally stored how in any default Parquet file it's stored. So for this ID column in statistics section, minimum value will be obviously 5, maximum value is 20. Then same for this file 2, if you consider ID column, minimum value is 10, maximum value is 70. For this file 3 ID, if you consider minimum value is 2, maximum value is 45, and for the file 4 minimum value is 10 and maximum value is 90. So like that way there are 4 small files available in our Delta. And suppose I want to query select star from table where ID equal to 12, right? Now ID 12 may fall under this range also, because minimum is 5, maximum is 20, so 12 is falling within this min max range. So file 1 cannot be skipped. Same goes for file 2, because min is 10 and max is 70. Within this range 12 falls. Same goes for file 3 and same goes for file 4. So because the data points are overlapping within various files, so to get the row for ID 12, we need to scan all 4 files. Data skipping is not possible in this small file data lake. Okay, even suppose you have applied bin packing optimization, right? And you have compacted your data. And now after compaction, you are having only two large files, one combiningly file 1 and file 2, one combiningly file 3 and file 4. Okay, basically bin packing does 𝐾𝐻 operation kind of thing in PySpark, if you recall. So suppose you are having multiple small files, and in our optimization bin packing in DeltaLake, generally we consider a 1 GB of space. Now in 1 GB data, whatever files can be accumulated, that it will accumulate. For example, out of this 1, 2, 3, 4, 5, 6, 7, out of these 7 small files, suppose combiningly 4 small files, it became 1 GB. So one bigger file will be having size 1 GB, and then rest 3 files will be creating another large Parquet file post compaction. So that's how simple bin packing compaction works. And now let's consider post optimization using bin packing approach or native approach. We are having two large Parquet files combiningly file 1 and file 2 and file 3 and file 4. Okay, so if you observe file 1 data 58920, so that I have written here, and file 2 data is 10, 15, 30, 70. So that I have written here. So now in this particular Parquet file post compaction or post optimization, we are having these all IDs. So if you consider the statistics again in the transactional log section in our DeltaLake, for this particular ID column, it will be storing min value 5, max value 70 for this part. And for file 3 and file 4, if you combine and get the statistics, it will be having min value 2 and max value 45, right? So now in this optimized DeltaLake, where basically tried to resolve this small file issue, there if you execute this command select star from table where ID equal to 12, still you will have the same problem that both of this large file it need to scan, because this ID 12 is falling within the range between 5 and 70, as well as it is falling within the range 2 and 45. Okay, it is not possible for Spark to ignore a complete file, right, due to this overlapping interface in bin packing based optimization. And that's the problem what z-order optimization solves. It not only compact the data and resolve small file issue, but it combine the data intelligently in such way that data scanning operation can skip as much file as possible. It will try to group the similar data in a particular Parquet file, and it will try to reduce the overlapping of this kind of nature. So that way, obviously it will help in data skipping, and obviously in turn the query execution will be faster. So let's see what we might observe in case of z-order optimization. So same small Parquet files, if suppose we are having with the same min and max range, and this time instead of default bin packing optimization, if we are applying z-order or z-order optimization, it will try to compact or rearrange the data in such way that similar data will be available in same location in sorted manner, and it should result into highest amount of data skipping while reading the data. For example, if you observe post z-order optimization, suppose we are having two files generated just like bin packing, but this time the IDs are arranged. In bin packing, simply it was combining file 1 and file 2 in one place and file 3 and file 4 in another place. But in z-order optimization, you will not able to see certain pattern. For example, here in one particular file, ID 2, 5, 6, 8, 9, 10, 10, 12 will be available. So if you observe these IDs, these are not coming from two complete files or three complete files like that. Some IDs are coming from one file, some IDs are coming from another file, and it is trying to sort the data and trying to place similar data in one particular file. For example, the ID 5 is coming from file 1. For example, ID 2 is coming from file 3. ID 6 is coming from file 3. ID 8 is coming from file 1. ID 10 is coming from file 2. Like that way, in a file, it is trying to group the data. Okay, following that same manner, another large Parquet file post compaction will be having rest IDs. Suppose this is kind of a scenario. Now if you observe, the minimum and maximum value with respect to statistics point, they are not overlapping for this ID column. Because in this particular Parquet file, minimum ID is 2, maximum is 12. For this particular Parquet file, minimum is 15, maximum is 7. And now if you apply same SQL query, that is select star from table where ID equal to 12, now this time due to the z-order optimization, this complete Parquet file can be ignored. Because based on statistics, we can clearly see that minimum value is 15 in ID column in this Parquet file, and we are looking for ID equal to 12. That means for sure this particular file will no longer be needed. That is basically based on statistical information from DeltaLog itself, we are completely skipping this particular file. We only need to work with this Parquet file, whatever we have achieved after compaction. So in short, we can say overall z-ordering helps your queries run faster because it makes it more likely that data can be skipped. And this is the simple concept of z-order or z-order optimization. That is, it not only resolve the small file issue, but it try to improve your DeltaLake query performance using the data skipping feature as much as possible. Okay, and if you want to apply the z-order optimization in your DeltaLake using programming, obviously you can check the code base here. This is the official documentation related to z-order optimization in DeltaLake. So earlier we have applied bin packing optimization using this simple command. First we have read the data using our DeltaSpark module, and then DeltaTable.optimize.execute compaction. If we are mentioning nothing, that means it will simply apply bin packing compaction. But if you want to apply z-order optimization, then this is the syntax. DeltaTable.forPath, using this way you can create a delta data frame, then .optimize.execute z-order by, and then based on which column you want to apply z-order optimization, that you need to provide. Like here ID1. Not only on one column, but you can apply z-order optimization on multiple columns also. Like here you can observe, execute z-order by multiple columns. Okay, and if you observe here, they have given the statistics also after running this comparison on a huge volume of data. Initial DeltaLake with small file issue is having this much runtime. This x-axis is seconds, and then after bin packing optimization, it is having this much time taken for queries. So obviously there is some reduction because it is at least resolving the small file issue. And if you are applying z-order optimization, then drastically runtime is reduced and query performance is increased, right? So I hope in this particular section, the fundamental concept of z-order optimization using theory and practical is clear to you. This is all for our this section. We will catch up in our next section with some more interesting concept related to DeltaLake, which will be useful in building data engineering pipelines. Stay tuned. Hello friends, welcome back to another new section in our DeltaLake course. And in this particular section, we are going to explore the concept of schema evaluation in DeltaLake. Okay. So before going ahead with this particular section, you should have some idea around schema on read, schema on write, etc. concepts, on which I have already discussed in detail in one of my previous video. The video link I'll be providing in the description box, and I'll request you to go through that particular video first to understand this particular section in detail. So DeltaLake utilizes the technique from transactional data warehouse called schema on write. This simply means that there is a process in place to check the schema of the write against the table prior to the write operation being executed. So in simple words, we can say, suppose you have already one table defined with 4 columns and you are writing a data with 5 columns. Generally in any transactional database or data warehouse, it will fail because the data what we are trying to write and in the destination data warehouse or in database, whatever table schema we have mentioned, they are not matching, right? That's why it generally fails. And that is the fundamental concept of schema on write. On the other hand, in case of schema on read, the concept is whatever data schema you want to write in the system, you write that way. While reading the data, it will be casting or selecting the required columns based on defined schema, which generally we achieve using Snowflake, variant, data type, etc. So in case of DeltaLake, it utilizes schema on write. That means if you have already one schema defined, you have to obey that schema while writing the data. You cannot follow some other schema in that case. For example, here I can quickly show you the demo. I am creating one dummy Spark data frame. I am showing the data and I am writing this data in a new DeltaLake with IDs data delta 5. As of now, if you check our DeltaLake location, here we are having couple of DeltaLakes. For example, IDs data delta, IDs data delta 4, IDs data delta 3, IDs data delta 2 and so on. But we are not having IDs data delta 5. For this particular demo, we are creating IDs data delta 5 and we are going to create a delta table also pointing to this S3 location, and that is DeltaLake DB.deltaTable 5. As of now, in our this DeltaLake DB database, if you observe, delta table 5 is not available. Only these 5 tables are available, but not delta table 5. So what we can do, we can run this particular job. Okay, sorry, I forgot to execute our first cell in Glue notebook, which basically configured the required file format and catalog for DeltaSpark module. So I think this particular process will fail, but still let's see. And here you can see it is failed to find data source delta. and that is obvious because here the first cell need to be executed which configured the required stuffs for our Delta Lake. So here you can see it is throwing an warning, no changes will be made to the current session that is set as do ETL. The session configuration will be applicable with the newly created session. So I need to stop this Spark session for 1 minute and then I will be creating this again. So first of all I will be going to my required cell and this is schema evaluation. So as part of the first step what I will do, I'll be stopping the Spark session once. And to do that, I can execute stop session and let's run it. Session stop, and now maybe I can run this particular stuff. See, waiting for session to be created, and here you can see the data frame is printed due to this df product.show, and we can hope that the data write operation is also successful because this cell execution is complete. So if I refresh my bucket, here you can see id delta 5 folder placeholder is created, and within this our actual folder is also created where we are having actual data points and the delta logs also stored. Right, perfect. Up to this it is pretty much simple thing. And now what we will do, we will be reading the same data using spark.read.format delta. Just now whatever we have written, we are adding one new column, one dummy column read 5. So I am adding a constant column with the name one dummy column, and there I am putting constant value 5 and I am doing df2.show. This is how the data looks like. And now I will try to append this particular data frame in the same path in the same table. Okay, data 5. And now let's see what happens. So here schema is changed. We have added one new column, and that's why you will observe that here one error is thrown. Analysis exception. The schema mismatch detected while writing to the delta table. The actual table schema is product ID, product name, price, category updated at, that is whatever we were earlier having, product ID, product name, price, category updated at. But the data what we are trying to write, that is having one new column, one dummy column. And due to this particular column, whole write operation is failing because Delta Lake follows schema on write. And now to resolve this particular problem, for example, in some source system, one new column is added and that we want to add in Delta Lake. So we have to use dot option merge schema. This particular feature need to be added. This will modify the schema and help in writing the data frame data. But before that, let me open Athena console and show you how it is getting displayed with respect to delta table point of view. And here I will be searching Athena. So here database I have chosen DeltaLake DB, and here you can see our delta table 5 is there. And now here I can execute simply this column. See, let's start from delta table 5, and here if you inspect, currently it is having product ID, product name, price, category updated. Now with this modified schema, if we want to write the data, this pattern we have to follow merge schema 2. And we are appending this data, so no data will be deleted. Whatever earlier was existing, some new Parquet files will be created. Okay, so if I refresh our delta log transaction, and maybe I can download and show you. So here if you see, all are add activity. Here it is add activity, here it is add activity, here add, here add, here add. Everywhere add activities because we are appending the data, correct? And this time if you observe, the data is written properly without showing any error. Due to this merge schema true, automatically schema evaluation happened in the back end, and now the delta lake is having that new column, one dummy column. So maybe if I query my Athena table now, post write operation, here you will be able to see that one dummy column is added. For the earlier rows, initially whatever we have written, for those this particular column was not even existing, so automatically delta lake is considering these are null values, and for the newly inserted records, for whatever rows we have given read 5, that means constant value 5 we have added for those lists, correct? So this is how schema evaluation is happening. And now I want to show you alternative approach. If suppose you don't want to apply automatic schema evaluation and want to apply schema changes in a controlled manner, that time what you can implement, that let me show you. And it is a very simple thing. That is, when we use dot option merge schema true to modify the behavior of DeltaLake write, it comes at the price of our not being fully aware of the changes to our table schema. That means when you are applying this, whatever new columns you have added or maybe data types you have changed, automatically all those will be applied on our DeltaLake schema, or schema evaluation will be happening in that manner. We will not be completely aware that what all changes it has done. But suppose sometimes this can be a very risky thing from business point of view. Maybe we want to do schema evaluation, but we should have more awareness or control on the change schema. If there is some schema change which is beyond our expectation, then schema evaluation should fail. That kind of controlled schema evaluation if you want to do, then merge schema true is not a good option. And that time how to perform schema evaluation, that let me show you. So first what I am going to do, same manner experiment, that first I am going to read the data from this folder, id data delta 5, which is having this kind of data as I already shown you in Athena. Same thing, some previous rows for one dummy column it is having null, and for the latest rows it is having value 5. And now here what I am doing, I am adding another dummy column with constant value 10. Okay, and now suppose I want to write the data in normal manner, so obviously again it will fail because schema is changed and DeltaLake will apply schema verification during write operation, and that's why it is failing, and it is clearly showing that is schema mismatch detected while writing to delta table. And here you can see the table schema is this one and data schema is this one. Here another dummy column, this is a new column what is added, that's why write operation is failing due to DeltaLake schema verification, correct? And this time we need to apply schema evaluation, but we want to do in a controlled manner. We don't want automatically using merge schema to all the schema evaluation should happen in the backend. But suppose you want to do in a controlled manner, that time what you can do, you can execute alter statement, how you change the schema in transactional database or data warehouse system following that same manner. Like here alter table, then database name dot delta table name. And suppose from business team you came to know that one new column is added. That's why in your Spark data frame also this column is available, and you want to add this in DeltaLake. That time you can simply execute alter table name, add column name and its data type. That way you can simply change the schema of our delta table beforehand, before write operation itself, right? So now I'll be showing you that, but before that let me show you in Athena. As of now, if you observe, if I just run this particular query again, here we are not having that another dummy column, and now here I'll be adding this one is a simple Spark SQL transformation, and here you can see the cell is getting executed and it is done. And now if I run this particular job again, here you will able to see another dummy column is added, but because for our existing data this column is having no value, that's why it is having null in all the rows. And now you can simply write your data frame in your existing DeltaLake, and you no need to provide merge schema true. So if I run this one, here you will be able to see data write operation is complete. And now if I execute this particular same code again, see, let's start from delta table 5. Here you will be able to see for some rows in another dummy column data is available just now whatever we have written. Okay, so this is how using controlled manner you can perform schema evaluation in your DeltaLake. This is a very important feature that DeltaLake always verify this schema before write operation, and that is basically schema on write. So this is what we have explored in our this particular section. Try to practice this particular lab. We will be catching up in our next section with some more interesting concepts. Stay tuned. Hello friends, welcome back to another new section in our DeltaLake journey, and today we are going to explore the concept of table restoration or rollback. So DeltaLake generally support insert, update, delete all these possible transactional operations, and suppose you need to delete some sort of data from your DeltaLake and you basically want to execute delete from table where, and then you want to provide certain filter condition, right? That way certain segment of the data from your DeltaLake should be deleted. But suppose by mistake you forgot to provide where clause and just the query is executed delete from table. So that way complete table data is impacted now. Now obviously in this kind of context, there should be some rollback mechanism available. And this you can achieve using DeltaSpark module. How? That I have written here. So first we need to import DeltaSpark module from delta.tables import start, and then we need to create a delta data frame pointing to our DeltaLake location. So already in our previous video we have created id data delta 5. This particular folder where our delta lake was sitting, right? If you just recall. So here first we have created one delta lake which is having schema, product ID, product name, price, category and updated at pointing to this particular location. Then as part of the next transaction we have added one dummy column with constant value 5. Then as part of the next transaction we have added another dummy column with constant value 10, right? So these are the major operations what we have performed in IDSData delta 5 folder where our delta lake is sitting. So to perform table restoration, first you need to create a delta data frame pointing to our delta lake. So to do that, first I need to execute this first cell, and then here I'll be scrolling below, and then here I'll be executing this cell. So here Spark session is going to be created. Just we have to wait for a few minutes. And obviously if you correlate this particular concept with Snowflake time travel, I hope you will be finding a lot of similarity. And Snowflake time travel also has some sort of retention period. Within that retention period only rollback is possible. Following that same manner, delta table also will be having some retention period. Within that you can safely perform table restoration. Regarding table restoration period and deleting the unused old files beyond table retention period, on those I will be covering in my next section. As of now, let's focus on table restoration. So here you can see session is created. Now let's wait for this particular cell execution to be completed. And this cell execution is done, right? Now here if I execute dt.history.show to observe all the historical operations done, here if you see, as part of the first step we have created the delta lake and we have inserted the data. Okay, then as part of the next step we have done certain operations by adding one extra column and mark schema true. Then we have basically executed alter table command to add one another column, and then we have written the data with another new column which is having the name another dummy column, right? So these are the major 4 transactions. Now suppose you want to restore to some old version. For example, if you recall, our current state delta table is having these columns, right? Like product ID, product name, price, category, updated at one dummy column, another dummy column. So another dummy column we have added as part of our last transaction. So suppose I want to restore back to one dummy column, which was the second transaction done in this delta lake, correct? So basically this particular step. So suppose I want to go back to that particular version. So I just need to execute dt.restore to version and then version number we need to provide. So that way our delta lake will be rolling back to that particular version itself. So I can execute this one. And here the cell is getting executed. And here the execution is completed. So we have restored to version 1, where basically we have added only one dummy column, not the second dummy column, that is another dummy column 1. So that way the delta table structure also should have been changed. Currently if you observe, if I sort based on ID, it is having 20 rows. But another dummy column data will be deleted and this column itself will be completely removed because we are rolling back to previous version. And here if I query my delta lake again, you will see that in our delta table only 10 rows are available and another dummy column is removed. Suppose you want to restore to version 0 where no dummy column was available. That also is perfectly possible. Just you need to execute dt.restore to version 0. And here execution is done. Now if I go back to my delta lake and run this query again, here you will be able to see one dummy column is gone and only that data is available whatever we have inserted in the beginning, right? So this kind of command restore to version and then provide the version number often helps in recovering the table if some kind of query by mistake you have executed without some where clause or something, and that might have impacted huge volume of data. That time to perform rollback or table restoration, this command is very helpful. That's why I thought to cover this one. Try to practice this, play with this, you will be having better feeling out of it. We'll be catching up in the next section. Stay tuned. So before going ahead with our next section, I want to draw your attention on one interesting point in Glue data catalog, especially for our delta tables. Okay, so here I have opened my Glue data catalog, and for this complete course here, the database what we have created is DeltaLake DB. Within that, if you go, here multiple delta tables we have created. If you pick up any delta table and observe the schema, you will be able to see that it is having only one column with the name call and data type array. If you check any other table, for example delta table 3, here also you will be able to see the same thing. Okay, but whereas if you go to Athena
and maybe if you try to do select star from here delta underscore table, and if you run this query, here you will able to see proper schema like id, sepal length, sepal width, petal length, petal width, class name properly we are able to see, right? That means in short I can say that in glue data catalog the schema is not properly getting populated, and sometimes you might get confused after observing this kind of thing. So in this particular section I just want to make you aware that this is a known issue, and already there is a GitHub issue open. If you observe catalog implementation for AWS glue data catalog, and if you observe in the motivation section, the first issue whatever they are describing is the DeltaLake schema cannot be recognized, and as a result it is automatically falling back to column of array data type, right? So the developer teams has already raised the concern, and now maybe the DeltaLake developer team need to inspect this particular issue and bring some resolution in their next release, right? So this particular issue is an open issue till now, but from our development standpoint or POC standpoint, this is not going to impact, because anyway whether you are reading the data using Spark or Athena, you will able to see the column names properly. Only thing is in glue data catalog it might not able to show you properly. That's all, right? So this is all what I wanted to share with you in this particular section. We will catch up in the next section. Stay tuned.
Hello friends, welcome back to another new section in our DeltaLake journey, and today in this particular video we are going to explore the concept of Parquet file to DeltaLake conversion using DeltaSpark module. Okay, so already in our previous video we have explored DeltaSpark module in detail, and in our last section we have explored how we can restore our table from a specific old version using DeltaSpark module, right? That is just using DataFrame.restore2 version, and then we can provide the version number. That way to that specific old version the table can be restored. Now let's see another application of this module, that is Parquet folder to Delta conversion. Okay, and if you think for a moment that there is a S3 location where all the Parquet files are available and we have to convert that to Delta, it is kind of a pretty straightforward stuff, right? Because if you observe any DeltaLake, for example Irish data Delta, where our DeltaLake is available, there all the data files are actually of Parquet nature. Only the difference in between Delta folder and a Parquet folder will be this Delta log folder, right? That is in DeltaLake, there will be a Delta log folder which will be capturing and storing all the transactions. That's the only difference. Rest, data-wise, if you see, in DeltaLake also data is stored as Parquet file format only. So that way, I hope you are getting this concept that Parquet folder or Parquet location to DeltaLake conversion will be pretty simple stuff. And that's what our DeltaSpark module supports. So let me quickly show you that. So for this particular demo, if you want to explore in detail, you can refer this particular documentation link, which I'll be providing in the description box. So here to show you the demo quickly, first I am creating a Parquet folder location, okay, with some dummy data, and the Parquet location name is id data delta 7. So if you see currently in our this particular bucket, here if I do a comment if id data delta 7, it is not existing, right? And then I am creating a table also in our glue data catalog. So if I just open my database in a new tab, DeltaLake DB, here delta table 7 is not available, right? So here what I will do, I will quickly run this particular cell to write the data in Parquet file format, and here you can see it is waiting for the session to be ready, and once session will be created, it will be writing the data in this particular folder location in Parquet file format, and session is created, and here data is visible now. So we can hope that if we refresh our bucket and if I search for id data delta 7, here you can see the folder is created within which our Parquet files are currently stored, right? Now I need to convert this to DeltaLake. So as of now in our this particular Parquet folder location, there is no underscore data underscore log folder is available. So that will be created once this Parquet location will be converted to DeltaLake, right? But I think I forgot to exclude the first cell, which will allow us to run DeltaLake related code in glue. So for that what I will do, I will quickly stop this particular session, and session stopped. Now I can run this one. The first cell is must, and then I can go back to my cell where I was explaining. So here if you see, I have written same thing what I just now told you, that since a DeltaLake table composed of Parquet files internally, the transaction logs is the biggest difference when converting to Parquet table to DeltaLake, because both basically in the backend storing the data in Parquet file format only. Just if you convert the Parquet location to DeltaLake, the delta log will be created. And if you think wisely, here all the Parquet files, once it will be converted to DeltaLake, all will be insert activity. So one delta log folder will be created, within which there will be one transaction where we will be able to see that all these Parquet files are basically getting added, right? So that also intuitively I hope it is clear to you. And to convert from Parquet to Delta, this is the command, that is using SQL. If you try to do convert to Delta, and then here our glue data catalog database name dot table name, whatever Parquet file and table we have created, right, in glue data catalog, that particular thing, if you convert from Parquet to Delta, this is the code, convert to Delta. And I'll just execute this one. So it is going to take few minutes, and we should be able to see once this cell execution is completed, here with underscore delta underscore log, one new folder should be created, and there one transaction should be available, which will show that all the Parquet files are basically added. So you'll observe that. And here you can see this execution is completed. Now if I go to my Parquet location and refresh, here you will be able to see delta log folder is created as we thought, and here there is 0.json is created. I can download this one, and here if I open my JSON, here you should be able to see that 1, 2, 3, 4, 5, 6 Parquet files are basically added. And if you observe, all these Parquet files are nothing but Parquet files whatever earlier itself available in this S3 location, right? So all those are added. So this is the simple way to convert any Parquet location to DeltaLake. Now this particular transformation we have done using database name dot table name. Now you can do the same using S3 path directly. So like earlier I have shown you, right, that any DeltaLake location you can access using delta dot and then S3 path you can provide. Like if you just recall earlier discussions, like this way we have accessed the DeltaLake data, right? There is one using database name dot table name possible. Another possibility is delta dot S3 path. So this kind of approach also you can follow while converting Parquet location to Delta location. So that let me show you. So earlier we have seen this approach. Now let me create one particular Parquet folder location to a new path, and that is ID's data delta 8. Although I have given the name delta in it, but it is basically Parquet files only. If you see that we are writing the data in Parquet file format, and save as table, if you observe, this is basically going to create a glue data catalog table as well in our DeltaLake table. But initially it will be in Parquet file format. Okay. So here you can see this cell is getting executed. If I go back to my this location, here ID's data delta 8 is created. As of now, this is Parquet. So there is no underscore delta underscore log folder is available, right? So this cell execution is done. Now to convert this particular Parquet location to Delta, earlier we have used database name dot table name from glue data catalog, but you can use in this manner also. That is convert to Delta and then Parquet dot Parquet folder location. Like how earlier we have referred Delta location using Delta dot and then S3 path for Delta location. Similarly here you can follow convert to Delta, then Parquet dot Parquet location. So that way this particular Parquet folder will be converted to DeltaLake. So if I just refresh, here you will be able to see the underscore delta underscore log location is created, where we are having only one transaction, and again this also will be having all things added, because this particular transformation we are doing for the first time. So all the Parquet files will be basically getting added in Delta. So that's what is happening, right? Pretty much obvious. Okay, cool. Now we are going to observe converting partitioned Parquet table to Delta. Okay, so as of now, whatever demo we have seen for Parquet to Delta conversion, there in this particular location we were having data which are not in partition format. But what we need to change when converting Parquet to Delta, if the Parquet data is partitioned, that we should see. So for that, what I am going to do, I am going to create a partitioned Parquet folder. So for that, first I am reading some CSV files from ID's data, and I am basically partitioning the data based on class name, and I am writing in a new location ID's data delta 9. Okay, as of now, if you see,
in our DeltaSpark testing in this bucket ID's data delta 9 is not available. So I am basically going to create a Parquet folder which is in partition format, and it will be having a blue data catalog table as well, which is having the name DeltaLake table 9. So this particular location let me create to show you a fresh demo. So here it is done. Now if I refresh here, ID's data delta 9 is available, where if you see our ID's dataset is splitted into different partitions and data is stored. For example, ID's 𝒂𝒂, there one Parquet file is there, then ID's 𝒉𝒐𝒂, there one Parquet file is there, and like that, right? So this time, suppose your Parquet location is partitioned and you need to convert this to DeltaLake. How you can do? So first approach is remaining same, whether the data is partitioned or not. That if you are referring glue data catalog database name dot table name, the syntax will be same, that is convert to delta. What is the default thing we have to write, and then database name dot table name. Okay. So basically what I'm trying to say, in partition format and as well as unpartitioned format, for both cases, if you are trying to use the glue database name dot table name, then there is no change. Okay. So if you go here you will see DeltaLake folder will be created newly, where this is a new transaction. If I download, you will see that here all are added, and if you see, the DeltaLake is also having partition column as class name. Okay, even if you go back to our glue data catalog and refresh our database, currently we are working with delta table 9, right? So if I go to delta table 9 and if I go to advanced section, if I scroll below, here you will see source provider delta, right? So from Parquet delta conversion happened. Now let's see how the code will change when instead of glue database name dot table name, we will use S3 path based approach. That is like here we have used, right? That is convert to delta is same, but if we want to use path based approach, then we are providing Parquet path, and before that we are writing Parquet dot. Will this be same or not? Let us try to explain. So for that, again I am writing the data in another new Parquet folder with ID's data delta 10. So here if I go here, so ID's data delta 10, this folder is created within which data is created with class name. Okay, cool, right? Now suppose that particular folder we want to convert to Parquet like earlier code. So just we need to write convert to delta and then Parquet dot our S3 path ID's data delta 10. That is basically this particular folder. And if you execute this particular command, you will see one error, and that is analysis exception expecting 0 partition columns but found class name partition column. That is, if you are using S3 path like this way to convert a Parquet location to delta, and if the S3 path is having partitioned data, then this code will not work. And that is mentioned what in this particular documentation also. That is, if you are converting Parquet to delta using tables, this command will be remaining same. But if you are using S3 path, then if the table is partitioned, then you have to mention partition by which column and its data type. So here I need to use this time partitioned by class name, and class name, as you know well, that in ID's dataset class name is having string data type, so I need to pass string. And now I can easily transform this. If I just run this code, in ID's data delta 10, if I go and refresh, here you will be able to see beautifully DeltaLake folder is created. That means now this particular Parquet location is converted to delta, right? So I hope concept is pretty much clear to you. That is, the syntax is pretty much same, convert to delta, and then you can give directly glue data catalog database name dot table name. Now always it will be converting from Parquet to delta, no matter whether the location is having partition data or complete data. But if you are using S3 path, using Parquet.S3 path that you are using for delta conversion, and if the Parquet data is in partition format, then you have to mention partition by as, right? That's pretty much simple thing. I hope you are getting it. So this is all for our this particular section. We will catch up in the next section. Till then, save this particular notebook and don't forget to stop it to avoid unnecessary cost. Stay tuned. Welcome back to another new section in our DeltaLake journey, and today we are going to explore the concept of vacuuming. Okay, so let us try to understand the concept of vacuuming with one specific scenario. Suppose we are having a DeltaLake. In this step 1 we are creating the DeltaLake and we are inserting some data in it. maybe using simple SQL insert into query, or that can be using Spark data frame write operation. Okay, we have created the table in Glue data catalog and we have inserted some data in it, which in the back end in DeltaLake created a file with the name file A. Suppose this is our actual Parquet data frame. Okay, so because this is the first transaction kind of thing we can say for our DeltaLake, so this will be considered as version 0, right? Then after few days we are doing some append activity. We are appending some data in it. So already in our DeltaLake file A was available. Now one more new file is inserted due to this append activity, and this particular version will be V1 version. As we know, we have seen also this earlier, that each time whenever you do some transaction, the version keep on getting increased by a value 1. So now in this particular step 2, in our DeltaLake, we are having latest version as V1. Okay. Now suppose in step 3, after few days, what you have done, using Spark data frame, you have executed an overwrite command. And by default, in any DeltaLake, what overwrite command does, it basically delete all the existing files in DeltaLake and write the new files, right? But in DeltaLake, as we know, that files don't directly get deleted. In the transaction log, maybe one new JSON file will be created where it will be captured that the existing files are removed and new file will be added. Something like that, it will be performing soft delete or logical delete and write the new files, but it don't do physical delete actually, which we have seen earlier also. So in override situation, in case of version 2, the DeltaLake situation will be like this. That is, file A and file B were earlier itself existing. So they will be kind of removed, kind of logical delete we can say, with respect to DeltaLake transactional log or delta log. And file C, due to this override operation, whatever data newly written, suppose let's consider that is file C, that will be added. Okay. So in the latest transactional log, 2 files will be removed and 1 new file will be added. Okay. These files what are getting removed, that means they are not contributing in current DeltaLake version, right? They are logically deleted. Those files are also called as tombstone file. Okay. So if you just search tombstone generally meaning in English, that is basically kind of this grave rock which we can see in graveyard, right? Where something related to that dead person is written. So same like that manner, if you observe, these files are no longer contributing to our DeltaLake. Kind of they are dead files. So they are also called as tombstone file. Okay. Now these tombstone files are not directly getting deleted from DeltaLake. And what is the advantage of this kind of soft delete if you consider? That is time travel. Same advantage what we generally observe in case of Snowflake Cloud Data Warehouse platform. That is, suppose for example, you have executed this override command by mistake. Now to roll back this particular transaction, we need help of these files, file A and file B. Suppose due to override command, if the file A and file B directly getting deleted, then we could never go back in past in a particular timestamp, right? Because those files which were contributing at that particular table state, they itself are removed. But in DeltaLake, they are not getting deleted. The only reason is to get the advantage of time travel. Now obviously with advantages, some disadvantages also comes. And in this case, the disadvantage is same like what we generally face while having time travel enabled in Snowflake. That is, if you consider you have created a DeltaLake and lot of transactions are keep on happening daily, then after 5-6 months down the line, lot of such unused files which are not contributing in current DeltaLake state, those will be still sitting in our S3 or any other cloud data lake system. And these kind of files will surely increase the cost of your cloud storage unnecessarily with time. So there is always a need for cleaning up these kind of unused files beyond a certain time. That is, for example, suppose this transaction is done today, right? So file C is created and file A and file B are softly untagged from our DeltaLake, but still they are existing in our S3 system. Okay. Now suppose one day passed and you want to go back to V1 state, that is basically roll back this override command. So that time you can do easily because file A and file B is existing. Then suppose 2 days passed with respect to this override operation. Then also if you want to go back to past V1 version, you can go. Suppose 3 days passed, suppose 4 days passed, like that way. Suppose 7 days passed, that is 7 days are completed after this override operation when file A and file B was detached and file C was attached. On the 7th day also, if you want to go back in past to V1 version, you can do that easily using time travel feature of DeltaLake, right? Now beyond 7 days
of any operation, it does not make sense to go back in past. Suppose you have done some transaction that impacted some file. Up to 7 days, I am giving you the flexibility to roll back. Now, in most of the business use cases, it does not require to roll back beyond 7 days and go back to past 7 days before. So basically what I'm trying to say that if any files are basically logically deleted, they can still be available in our Delta Lake for 7 days starting from that particular transaction. Beyond 7 days, we can delete these kind of files which are not getting utilized, or tombstone files we can delete. So that is basically default Delta Lake retention period. That Delta Lake says if you are creating any table by default, any transaction you do, the tombstone files which are generated due to those transactions will be surely available in our Delta Lake for at least next 7 days by default. And within that 7 days, you will have the flexibility to roll back. Okay. Now, if it is going beyond 7 days, then these kind of unused files we can delete from our Delta Lake system to keep that clean. And that is basically what vacuuming command does. So what it does, it basically helps in deleting the tombstone files from our Delta Lake. That is those files which are not currently contributing in our current Delta Lake state, and those files are beyond the default retention period what we have configured in our Delta Lake. Okay. So again, I am telling you, be very careful with respect to the retention period value. That retention period don't get start from when the file is written. Retention period starts from when the files became tombstone files. That is, the file A may be created 20 days before. Okay. But they become tombstone files in this overwrite activity. Starting from this day up to next 7 days, these files can be kept in our Delta Lake. Beyond that, using vacuuming command, if we want, we can delete these files. And that does not happen automatically. Vacuuming command does not get automatically executed. We need to execute the command. And this 7 days value, what is a default value, what I'm saying generally for any Delta Lake tables, that also configurable. Suppose based on your business requirement, you might need to time travel up to 30 days back in past. That thing you can control in table creation stage also, and even while executing the vacuum command also. That I'll be showing you while explaining the practical. Okay. So in short, till now we understood from this theoretical discussion that vacuuming command basically helps in deleting the unused tombstone files from our Delta Lake which are beyond our retention period. And the retention period is basically calculated starting from the transaction date. Okay. So obviously this vacuuming command can help in reduction of the cloud storage cost by removing these unused files. But again here also you have to be very careful before executing vacuuming command, because suppose after execution of this override command, after 7 days, you are executing vacuuming command in the Delta Lake, then automatically this file A and file B will be deleted from your Delta Lake. So that time, post execution of vacuuming command, you cannot go back to version v1, because the file A and file B which were contributing in version v1 for our Delta Lake, they are removed. So you can never go back to that past after execution of vacuuming command. So vacuuming command basically put a constraint on our time travel, right? Be very careful or mindful on that. And also one more point I would like to highlight, that vacuuming command never impact or never change the transactional logs whatever available in _delta_log folder. It just delete or play with the data files what are available outside _delta_log folder. Okay. So as a result, what will happen, we will observe this when I will show you the practical, that post execution of vacuuming command, if you describe the history in the table, you will still see the complete history. That is, though the file A and file B, the data files will be deleted due to vacuum command execution, but in Delta Lake history, you will still see that this append activity happened, this overwrite activity happened, etc. etc. That is, vacuum command only delete the data files, it never delete any transactional logs. This is another very important point, right? So with this basic theoretical understanding, we are ready to jump into the practical of vacuuming command, which I'll be discussing in my next section. Stay tuned. So welcome back to all of you in one of our new section in Delta Lake journey. And in this particular section, we are going to do some hands-on around vacuum command, related to which theoretical concepts we have already explored in our previous video. So just a quick recap, that Delta Lake does not physically remove files from storage for operations that logically deletes the files. That is basically Delta Lake don't delete those files which are currently not contributing to the latest version of Delta Lake. you need to use vacuum command to physically remove the files from storage that have been marked for deletion and older than retention period. So in our earlier section, I have told you, right? That is, suppose you have executed one override command and due to which some files are marked for deletion, then automatically it will not be deleted post retention period, which is by default 7 days. Using vacuum command, if you want, you can delete those. Okay. So the main benefit of vacuuming is to save the storage cost. Vacuuming does not make your query run any faster and can limit your ability to time travel to earlier DeltaLake versions, which is obvious, right? There is vacuuming command is basically deleting some files which are not getting utilized in our current DeltaLake. It will not improve the query execution time. Because anyway, from our transactional logs, when DeltaLake will try to read that which files it need to consider to return the data, these files will be automatically getting skipped. So it will not even scan the files whether they are existing in DeltaLake or not. Actually, for DeltaLake, it does not matter. So it will not at all improve the query performance, but it will save the storage cost. And as I told you earlier, it can limit your ability to time travel to earlier Delta table version. And you need to weigh the cost or benefit for each of your table to develop the optimal vacuum strategy. Okay, cost versus benefit, meaning if you don't execute vacuum command, you can perform time travel for a longer duration, but that time cost will increase. So you have to basically balance between cost and benefit. That's what I have tried to say here. Okay, so now without any further delay, here I will be creating a simple DeltaLake pointing to id_data delta6, this particular folder location. So if you see, currently in our bucket, there is no folder called id_data delta6. So I'll be inserting some data in it. Okay. So the data will be getting inserted, but I think I have done a mistake. I have not executed the first cell. So let me stop this Spark session and execute that. So I think this cell execution will be failing. And once it failed, we will stop the session and execute the required configuration command from our first cell so that we can use DeltaLake in our Glue notebook. So here you can see Java lang class not found, failed to find data source delta, which is pretty much obvious. And here I will stop the session. Session stop, then I no longer need this cell, I'll delete that. I'll be going back completely top and I'll be executing this particular required configuration. And then here I'll be going back to my vacuum command location here. So here first we are creating a DeltaLake. So here you can see that due to this particular show command, it is showing the data, and we can hope that the folder should be created. So here if I refresh, here id_data delta6 is available, within which our Parquet files are available perfectly fine. And now what I can do, I can execute some delete command. But before that, let me put a cell, and here basically I am trying to delete one data point which is having product ID 5. But before that, let's try to see which Parquet file is having this product ID 5. Okay, so here I can execute a simple command like df=spark.read.format delta.load, and here I'll be putting this particular path df.filter df of product id equal to 5, and then here dot select input file name dot show truncate equal to false. Okay, right? So let's execute. So product equal to, and here you can see that this is the Parquet file actually where our product ID 5 is available. So this is the Parquet file. Okay, right? So now what we can do, we can basically delete this particular product ID 5 so that one tombstone file will be created, right? So I can run this particular thing from our DeltaLake, Delta Table 6. So here you can see already we have created Delta Table 6, right? So number of affected rows is 1, right? Perfect. So even if you go to transactional logs, and here if I download the data, and here if I open this one, we can hope that this particular Parquet file is removed from DeltaLake. Let's see. So here you can see this is the file which is removed, which is pretty much obvious. By using input file name itself, we beforehand understood which Parquet file it should be removing. And based on our practical DeltaLake transactional log also, we can observe that DeltaLake has removed that particular Parquet file only. Now the question is this Parquet file is deleted from DeltaLake? Let's see. Here if I do a command F and if I search, this particular Parquet file is still there. That means it is now becoming a tombstone file. It is not going to be used by DeltaLake in its latest state, but it is still there, so that if someone wants, they can roll back this delete operation or perform time travel in past. Okay, right? Now, as I told you that by default, the data retention period for any delta table, if you are not configuring, then it is 7 days. Correct? Now, if I execute vacuum command, based on theory, vacuum command will not show any file to be deleted. Because although we are having a tombstone file, but that file is within retention period. This transaction happened just now, and just now this file became an unused file. Its retention period is not over. So if I execute vacuum command, it will show that there is no file to be vacuumed or deleted permanently from DeltaLake. So to run vacuum command, this is the syntax: vacuum, then DeltaLake database name from glue data catalog dot table name you can put, and you can put dry run just to get the list of the files what vacuum command should be deleting if it run. It will not actually delete the file if you put dry run command. It will just list the files, whatever it can delete if you actually execute vacuum command. Actual vacuum command is only this much. We are putting dry run to first get the list. Okay. So let's run this one. And here you can see it is returning no file path. That means there is no file currently available in our DeltaLake which are tombstone file as well as they are beyond retention period. Right? Because 7 days is not yet over with respect to our transaction. So that's what I have written here. The vacuum command won't actually delete any files because tombstone files are not older than retention period, which is 7 days by default for our this particular DeltaLake table. Okay. But now suppose, although we know that the default value for retention period is 7 days, but I want to control myself. While executing the vacuum command itself, can we control that I want to retain only this much hours of tombstone files or this much hours of previous transactions and rest should be deleted? That functionality vacuum command provides. And here is the code for that. Spark.sql vacuum table name, then dry run only I want to do as of now, and here I can provide retain 0 hours. That means it will only retain those tombstone file which became unused within this much range. Okay, suppose I am putting retain 20 hours. That means those all unused files which became unused within 20 hours, those alone vacuum command will be not touching. Rest all tombstone files, whether they are within retention period or not, it is going to delete. So that kind of functionality vacuum command is providing. Vacuum, then delta table name, then retain how much data, and then dry run. So this way I can kind of control the retention duration for the file deletion using vacuum command. Okay, so maybe I can run this one. So if I am running 20 hours, here you will see it is throwing one error. Illegal argument exception requirement failed. Are you sure would like to vacuum file with such low retention period? So that means DeltaLake is basically putting a warning. Whenever you try to retain files less than 7 days, DeltaLake will throw this kind of warning so that you don't do any mistake in execution of your vacuum command and unnecessarily lose the history. Okay, even if you put retain 0 hours for this demo, I need to keep retain 0 hours so that I can show you that this actual tombstone file is getting deleted. So for that, if I put retain 0 hours, then also vacuum command is throwing this error, and by default it is saying that retention period is 168 hours. If you calculate 168 hours divided by 24, that is 7 days. That is default retention period is 7 days. Vacuum command don't want you to change. But still, if you want to execute vacuum command, what you have to do, you have to change this property. That is, whenever vacuum command get executed, basically first it is checked whether retention duration criteria is satisfied or not. And by default, retention duration check enabled or not. If you check, it is enabled. That is true. That's why vacuum command is throwing an error. It is not executing any delete command in the backend. Okay, but suppose your table is having retention period by default 7 days and still you want to execute vacuum command with less retention period like this kind of command, then you can make this particular property to false. Okay, Spark Databricks delta retention duration check enabled false. And then if you basically try to execute the same command, that is vacuum, and then this particular table name on which just now we have executed a delete command and written 0 hours, and maybe first let me put try run, and then if I run, it will throw this particular Parquet file which is currently not used, and that ideally should be listing, because currently I am giving a command that I don't want to follow the retention period which is by default configured of 7 days. I want to retain only 0 hours data. That means I don't want time travel, and this I am doing so that I can show you how vacuum command is working in our Delta Lake, because I cannot wait for 7 days, right? So here you can see it has listed this particular Parquet file, and if you check in our Delta Lake, if I just search, you will observe that this Parquet file is this one only, right? That means just now due to delete command, whatever file became tombstone file, now vacuum command due to 0 hours retention, it is saying that it can delete. Now just remove the dry run, and that way if you just run this actual vacuum command, you will see that your this Parquet file will be deleted. So we'll run this one now, and here you can see that one file should be deleted. Just this Parquet file, if I just refresh and search, just refresh this, and if I do a search, here you will see that this Parquet file is no longer we are able to find out. And the reason is pretty much simple, that vacuum command has deleted that particular Parquet file. Now we can just have a history check. So spark.sql describe history. Basically I am executing the history of all the transactions performed in this particular table, and show truncate equal to false. Okay, so if I execute this particular command now, here you will see that first we have basically created the table, and then we have executed a delete command. That means transaction wise there is no change. This proves another important point what I already discussed during theory, that vacuum command only play with the data files. It never touch the transactional logs available in Delta Lake. Still in Delta Lake you are able to see this delete command, right? There is no change. And now in our next cell, I am going to show you another very important conclusion from our theory what I have discussed, that once you execute vacuum command, suppose in V2, that is file A and file B are gone. That means you can never go back to V1, because in V1 state file A and file B was used. So obviously you cannot perform time travel, right? So for example, in this particular case, suppose I want to go back to version 0. That means when I have basically created this particular Delta Lake, right? But I cannot go back because I have already executed the vacuum command, and due to which this particular file is gone now. This is not available in Delta Lake. So obviously I cannot perform time travel. So now if I try to execute this cell, that spark.read.format delta, and I am trying to go back to version 0, and if I execute this particular cell, here you will be able to see that job aborted during stage failure, and it will show you that this particular Parquet file it is not able to find out. And this Parquet file is basically same one. If you observe here, same Parquet file what just now was removed, right? So the conclusion is vacuum command restrict the time travel, and that's what I think I have written in the markdown, that VVI conclusion, if you run vacuum command on Delta Lake, you lose the ability to time travel back to a version which is older than specified data retention period. Okay. And also parallelly I want to tell you this very important point, that you should never go to Delta Lake and manually delete a Parquet file from here. That way Delta table might get corrupted, because in transactional log it is referring that this Parquet file it need to read or write in which state, and all those things will be messed up. If you manually try to corrupt any Delta Lake or some external system, you try to do some changes in Delta Lake, that time this kind of problem appears. That is, remember to never remove Delta Lake table data files outside the context of Delta Lake operations, as doing so can corrupt the tables. That means if you need to delete the tables, use vacuum command. Don't do it yourself outside Delta Lake scope. Okay. And as I told you, vacuum command is obviously helpful to control the cost of your Delta Lake. but it never run itself. So for your production system DeltaLake tables, to keep our Delta Lakes clean, you can set up a cron job to call vacuum command on daily basis or weekly basis, so that it will continuously keep on deleting those tombstone files which are beyond retention period, starting from the transaction when the file became tombstone, right? And now I am going to show you that particular property using which you can control the retention period. Instead of by default keeping it 7 days, you can put any value as per your requirement in the table creation time itself. And that particular feature is delta.delete file retention duration. Okay. And there you can put certain interval, that is interval 2 days, interval 3 days, like that. So this will basically control the retention duration for the deleted files. That is, post the retention duration, the files can be deleted using vacuum command. By default, this is 7 days. But if you want, while creating the DeltaLake table, you can put this particular property, and DeltaLake vacuum command will obey that particular thing. So to show you again this particular thing, I will just stop this Park session to show you this fresh demo. Stop session I'll be doing. Session is stopped. I'll be going back to the top, execute this first cell, and then here I will be going to completely bottom. And now here what I am going to do, I am going to create a DeltaLake table. Okay. But this time here I am mentioning the table properties that deleted file retention duration is 0 days. That means I don't want to do time travel. Suppose that kind of situation I am creating and pointing to this particular delta location, new delta location, delta table 11, right? So this is how you can mention the table properties and adjust the retention duration while creating the table itself. So here you can see our new delta lake is going to be created. Once our delta lake will be created in delta table 11 folder, I am going to insert some data in it. Okay, so that way our new delta lake will be created. And here I think the file is created. If I just refresh here, okay, it is refreshed and delta table 11 got created. Okay, cool. Now what I am going to do, I am going to delete. Okay, before delete I should have executed this particular statement that I should insert some data in delta lake, because just now I created the table but it is empty. So here delta lake data we are inserting, and it has inserted. Now I can delete some class name from ID's dataset, that is ID's particular. Suppose I am deleting. So 51 rows affected, that is fine. But now I can execute vacuum try run command on our delta table 11. Earlier for our delta table 6, when we have executed, that time vacuum command was listing nothing, because delta table was having retention duration configured as 7 days. But in this case, we have configured the table properties 0 days for deleted file retention duration. So just now some file became tombstone due to this delete command, and immediately I am executing vacuum command. So natural behavior should be immediately should be showing some files that vacuum command will be deleting, because here retention duration is set as 0 days, right? So that's why it is showing that this Parquet file it will be deleting. If I want, using vacuum command, I can directly simply delete the ID's particular deleted files what was actually deleted from our delta. Okay, so that way automatically the tombstone file for ID's particular will be deleted from delta. So in this particular lab section, what I basically tried to show you that you can control the table properties using deleted file retention duration while creating the DeltaLake table. Even if your table is already created, using alter table command, you can change the property of that DeltaLake table also. That particular command I'll be providing as a text here, and you can basically try to do experiment with the same and let me know whether it is working or not. So this is all for this particular video. I will catch up in our next section with some new interesting concept related to DeltaLake. Stay tuned. Hello friends, welcome back to another new section in our DeltaLake journey. And today in this particular section, we are going to explore how to work with DeltaLake and native Python. So till now, whatever concepts we have explored related to DeltaLake, those were mostly using SQL or PySpark using DeltaSpark module, right? But suppose your team is not using Spark, mostly using native Python, maybe the data is not very huge, maybe for that reason the team is using normal Python instead of Spark, and the team want to use the DeltaLake. That time there is a module called DeltaLake that you can utilize to work with Python and DeltaLake, and that is this one. Okay, so we have explored DeltaSpark module, which is required to work with PySpark or Big Data World. And if you want to work with DeltaLake and native Python, then you can install this particular module
all the operations till now, whatever we have covered, starting from reading the delta lake to writing the delta lake in override or append manner, go back to some particular division, time travel, optimization, z-order optimization, vacuuming, all these concepts this delta lake module also can implement. So I am not going to cover all the concepts again, but I am going to give you some sense of quick start. Following this particular notebook, you can basically try out other examples as well. So as a first step, what I am going to do, I am going to install Delta Lake in my Google Colab notebook. So let it get installed, and then here I am importing pandas. Suppose initially we are not having our Delta Lake, we are just having a pandas data frame, and as a first step we want to write that particular data as Delta Lake. So that time from Delta Lake.writer import write Delta Lake. This particular module you need to import, and then from Delta Lake import Delta Table. This particular Delta Table can help us in reading the Delta Lake data from some S3 location. Okay, so here installation is done. Now I can execute this particular command to import all the necessary things, and now here I am going to create a very simple data frame with element 0 to 4. And here you can see 0 to 4 elements are there because I have given range 5, that's why 0 to 4, and column name is ID. A very simple pandas data frame. Suppose I want to read this particular data as a Delta Lake in our AWS S3. So as of now, if you observe, mostly we have written the data up to Delta Table 11. Now maybe for this particular demo, I want to create a new Delta Lake with the name Delta Table 12 in our same S3 bucket. Okay. Now, before doing the write operation, we have to set up the authentication between Google Colab Notebook and our AWS account. So for this, generally we are using access key or secret key based authentication. So I'll be running this one. So this is how you have to configure the access key and secret key, that is storage options, and then you have to pass that as dictionary. In dictionary, there will be two major key: AWS access key ID, AWS secret access. Okay. And now if you want to write this pandas data frame in some particular S3 location as Delta Lake, then you can use this write Delta Lake function. You have to pass the S3 path first where your Delta Lake should be created, and then your pandas data frame what you want to write. Then storage option obviously you have to provide for authentication purpose, and modical to overwrite or append like how in PySpark we were using, that you can introduce. Okay. So just I want to show you again that if you go to this particular bucket and do a command def delta table 12 is not existing, right? So I'll be running my storage option first and then write to Delta Lake I'll be doing. Okay. So here the cell is executed, and now if I refresh this particular thing and if I search Delta Table 12, here you will see this folder got created. So this particular Delta Lake what we have created pointing to this particular folder is now created using native Python instead of Spark or S3. Okay, and obviously you can download this particular Parquet file. You'll be able to see using Parquet viewer that it is having same data whatever we have inserted. So here if I select this file and close this one, here you will be able to see ID 0 to 4 are available. Just now whatever we have inserted. Okay, even if you want to check the delta log, if I download this one, here you will be able to see in 0.json that one particular Parquet file is added, like how we have discussed earlier, right? Here you will see it is an add activity and this Parquet file is added. Okay, right? And now if you want to read that particular Delta Lake, existing Delta Lake, then you can basically simply use Delta Table function to pass the S3 path where your Delta Lake is sitting, and then for authentication purpose you have to pass access key and secret. That way you can read the Delta Lake table. Okay, so this will be kind of creating a delta data frame. If you want, you can execute the ed.history to check all the historical operations whatever we have done. As of now, basically we have just created this particular table, so you can see that operation is write, mode is overwrite, correct? Now if you want to view the data, you can use dt.head, but here you will be able to see delta table object has no attribute head. Okay, because dot head is a pandas operation, not default delta table. Like how earlier when we have created a delta data frame from DeltaSpark module, and when we were trying to do dot show, it was not working because dot show is belonging to Spark, not delta table, right? So what we had done that time, first we have converted that delta data frame to Spark data frame using .2df, and then we can execute dot show. Similarly here, if you want to execute dot head, first you have to convert this delta data frame to pandas, and then you can execute dot head to view the data, right? So using this particular module, I hope you are getting this, that we can write the data, read the data apart from history operation and all this. Okay,
And then here I have listed some important links which you can explore and perform some practical around different operations related to Delta Lake. For example, Delta Table optimization, if you open, here you will able to see the Pythonic approach for applying compaction using bin packing or Z-order optimization, etc. So like here, first you have to read the Delta Table and then .optimize, .compact you have to apply to perform default bin packing optimization to resolve the small file issue problem in your Delta Lake. But if you want to do Z-order optimization, you can perform using this kind of command. Then apart from that, next thing, if you see updating Delta Lake Table, like how we have used DeltaSpark Module to update some data, dt.update, and then you can put some clause for update clause. And then here deleting Delta Lake Table, if you see this particular link, using Delta Table.delete, and then some condition you can provide to delete certain rows from your Delta Lake. Then restoring to Delta Table version specifically if you want to do. Then here restoring table option is there. dt.restore, and to which version you want to restore, that you can provide. Okay, so that way vacuuming operation, merge operation, and complete documentation reference if you want to refer, then you can go to this link, right? So this way you can explore using this Delta Lake module how to work with Delta Lake and native Python. I hope this quick start will be helpful to you, especially if you are Python lover. So this is all for our this particular section. We will catch up in our next section. Stay tuned. Hello friends, welcome back to another new section in our Delta Lake course. So already in our previous video we have explored in detail about Delta Lake using Python. That is, using this particular Delta Lake module, we can easily work with Delta Lake and native Python instead of working via PySpark. So in this particular video, we are going to use this particular module in AWS Lambda function so that we can build a near real-time Delta Lake. So for example, here we are having one S3 bucket, and there we are having a landing layer, this particular folder. Maybe this particular folder in backend is connected with some AWS SFTP location, and now some users are uploading CSV files. Okay, once the files are uploaded in this landing layer, automatically in near real time, those CSV files should be ingested in our Delta Lake, which is available in this particular folder. So that time you can basically take help of AWS Lambda and this Delta Lake module to convert these CSV files to Parquet and ingest in our Delta Lake, right? So in this particular section, we are going to explore this particular concept in detail. So by default, this particular Delta Lake module is not available in our Python runtime. So we need to create a Lambda deployment zip file for that. Or another option can be, we can take help of ECR to create a Docker image, and we can create our Lambda function using that Docker image, right? So in this particular video, I am going to take the second route. That is, basically we are going to create a Docker image where all our required modules along with Lambda code will be available, and using the Docker image we will be defining our Lambda function. So if you check our Lambda function, it is a very simple function. We are first importing all the necessary modules. So specifically we need to read the S3 data from landing layer as a pandas data frame in CSV file, right? So we need to basically install pandas in our Lambda Docker image, and we need to take help of write Delta Lake, this particular function, to write the pandas data frame in Delta Lake, right? Like how earlier we have explored in this video, that write Delta Lake and then Delta Lake path, and then the pandas data frame we need to provide. Now another thing we have provided is storage option, because we were running the code from Google Colab, so for authentication purpose we had to provide this storage option. But when running from Lambda, this is no longer needed because it will be basically authenticated via IAM access policies, right? And mode we can provide append, so that way in landing layer whatever CSV files will be coming, the Lambda function will be converting to Delta format and keep on appending in Delta Lake, okay, instead of overwrite operation, right? So for that, write Delta Lake will be helpful. And if you check our main Lambda handler, here what we are doing first, we are printing the event whatever has triggered our Lambda function, and then table URL. So basically this particular thing will be defining that particular S3 path where our Delta Lake is sitting. In this particular case, our Delta Lake is available in this Delta Lake folder. So our table URL will be basically this Delta Lake S3 path. Okay, as simple as that. We'll be configuring this in environmental variable. And if it is not configured, we are raising an exception, that is fine. And we are printing that this is the table path where our Delta Lake is sitting. And then here how we generally parse S3 event, following that manner. We are extracting the records part, and then for each record I am extracting the S3 bucket and the key for which the Lambda is getting triggered, and then here I am printing that currently we are processing this particular file. Okay, next what we are doing, get S3 object. So if you check this get S3 object function, using this basically we are extracting the body part, okay, from our S3 file. So using get object, first I am getting the complete object, and using body key I am extracting what actually the CSV file contains, right? And then if you check the next step, what we are doing here, that we are reading that particular S3 data in a pandas data frame using this particular function, that is read CSV from S3. So if you see read CSV from S3, just we are executing pd.read CSV, that's all. Okay, now obviously next step will be write to DeltaLake. So we need to pass the pandas data frame what we want to write and our S3 DeltaLake location, that is table URL. So if you see the write DeltaLake, it is a very simple function. All it is doing is using write DeltaLake function, it is writing the pandas CSV data frame in our DeltaLake in append manner, right? And that's all. And then we are basically returning success for 200. If exception arises, we are handling that exception. So this is our Lambda function. So what I will do first, I'll be creating this Lambda function.py, and for creating this particular Docker image, we need to take help of GitHub. So here I have created a empty repository, and here what I will do, I will create a new file, and here Lambda function.py I'll be keeping. This is the complete code. I'll be copying and pasting. Already in our previous video I have explained in detail how to create a Lambda function from ECR Docker image, so you can refer that particular prerequisite video link given in the description box. So as part of the next step, we need to create the Docker file where this particular base image we need to use, and then here we are importing all the necessary modules from requirements.txt, and then we are calling our Lambda handler. So this Docker file also I'll be creating. This is the code base. So now we need to create the requirements.txt also. So what I'll be doing is part of my next step. Create new file requirements.txt. And here I hope from the code itself you can understand that pandas and DeltaLake, these two modules will be needed. Pandas for reading the S3 CSV file, and DeltaLake for write operation in our DeltaLake from AWS Lambda. And I'll copy this. Okay, right? I hope up to this it is pretty much clear to you. And now the next part what will be required is GitHub action. So this kind of GitHub action already we have executed multiple times. That is, first in Ubuntu latest we are running, we need to provide access key and secret key. So that I'll be creating here quickly. We'll go to security credentials. And here I'll be creating access key for other. Next, DeltaLake Lambda, some name I can give, and here is my access key secret. Ideally, we should not provide access key secret key as hard-coded value in GitHub action. We should be putting in secrets, but just for demo, I am using like this way. Now here, we need to log into ECR using this default action, and ECR repository, whatever I have used in our previous video, was having this name. I'll be changing the repo name, maybe DeltaLake Lambda white. Okay, so with this repository name, first I'll be creating a ECR repo. Create repository, and here I can provide the repo name. Okay, here it will be created. So here this repo is created. As of now there is no image in it. That is perfectly fine. So first here, as part of the next step, what we are doing, we are building the Docker image, pushing the Docker image, and earlier we have updated the Lambda function also. This one I no need to do, I will do it later separately. So this becomes our GitHub action code. I'll be copying this code, I'll be going to my GitHub and adding the files. .github/workflows/min.yaml, and here I can paste this code. Okay, right? And I'll comment the changes. So with this, one GitHub action should be starting, because here I have given that on each push activity this ECR image has to be created. So here you can see that create main.yaml, and here our GitHub action is running. And here it is completed. We can go to ECR, and if I refresh, here I can see the image what is pushed. Now from this image I'll be creating a Lambda function quickly. I'll be going to Lambda, and here create function. From container image I want to create Lambda function name real time delta lake, some name I can provide, container image. So this is the image ERN. I need to copy that, paste that here, and then execution role, create a new execution role. That is fine. As of now I can create this one. So here the Lambda function is created. I need to change certain properties like timeout. I will increase little bit. Okay, cool. And this Lambda function will be reading the file from S3, writing in DeltaLake. So for this kind of operations, obviously S3 access is needed. So that one also I'll be providing. So save this one. And then here I'll be going to permission. And in this role, I'll be providing S3 full access as of now, so that Lambda can freely interact with our S3 read-write operation it can do. Attach policy. You can search for S3 full access. I'll add this permission, and it is added. Okay, cool. Now next step is adding the trigger. So here I'll be quickly searching S3, and from this particular bucket the trigger should be going, this one, and I want to trigger only those events whatever is coming in this landing layer. So we'll be copying this and then paste in this prefix, so that landing layer related events will be triggering this Lambda. Recursive invocation I will not do, and I will simply add this one, right? So with this our primary setup is ready. Now what we will do, obviously we can expect that once a CSV file will be landed in landing layer, this Lambda function will be triggered, which will write the data as a delta format in our delta lake. So now to query this delta lake, I will create a Athena external table pointing to this delta lake. So that also let me do quickly. So this is our Athena, and here I am creating a very simple delta lake table. Create external table delta lake db dot lambda delta, and here I am pointing to our delta lake location. Okay, that is S3, and then bucket name, and then delta lake, and table properties table type delta. This is how you have to create an external table pointing to delta lake using Athena. You no need to provide this schema. Automatically Athena will infer from the delta lake transactional logs. So here I can create this particular table. Okay, so here you can see it is throwing no delta table found at this particular path. Maybe first it need to have some data. As of now you can see in our delta lake there is no data. So first let's run our Lambda function and let's see whether our delta lake is getting created or not, and post that we can create this Athena table, not a problem. But before running our Lambda function, I need to do one more thing, that is in environmental variable I need to configure my delta lake. So value will be this one, and the table environmental variable name we are going to take from here, right? This table URL, this one we are using. These things are pretty much simple things, so I am just running quickly. And now here we are ready to start the experiment. I'll be taking some sample 𝒁𝒂 𝒁𝒂 versicolor file. So first maybe I can upload a sample 𝒁𝒂 file here, and I'll click on upload. File is uploaded. We can go to monitoring for our Lambda. And here you can see Lambda log is created, that means got triggered in real time. And here successfully read the CSV file with 27 rows, attempting to write the delta lake. So, and successfully process this particular file. That means if we go to our Delta Lake and if we refresh, we can hope that our transactional log along with our Parquet data is created. So this is how Lambda is creating the Delta Lake. Okay, again the default behaviors you can observe. You can download this particular transactional log and you will see that here basically it will show that a Parquet file is added. So here you can see only one add activity is there, and if I copy this particular Parquet file name and here if I search, you will see this Parquet file is there. Now I can create Athena table pointing to that location and perform select star from that Athena table. If I run this query, here you will be able to see our data properly. Whatever 𝒉𝒂𝒂 file we have uploaded, that is visible. So maybe let me upload another file. Maybe 𝒉𝒐 color I can upload. So suppose using 𝒄𝒓𝒕𝒂 or something, some customer has uploaded 𝒉𝒐 color. Immediately in near real time, it will be ingested in Delta Lake. So here you can see currently it is 9:50 PM and at 9:50 this file is added. Okay, if you go to Delta Lake logs and if you download this second transaction, you will see that this is also an add activity, and whatever file is added for that particular file, if you observe the class name column which is available here, for that the minimum value is also 𝐼D_𝒔 color, and if you check the maximum value for the same class name column, you will see that is 𝐼D_𝒔 color. So minimum value 𝒔 color, maximum value 𝒔 color, that means overall in the data only 𝐼D_𝒔 color class is available, whatever file we have just now ingested. And even if you want to check using Athena, if you run this query again, this time in the class name column, if you sort, you will able to see after 𝒉𝒂𝒂 𝐼D_𝒔 colors are available. So this is how using this Delta Lake module and Dockerization concept, you can build real-time Delta Lake ingester using Lambda function for your project, right? I hope you understood this. The complete code base as usual I'll be providing in the description box. Try to play with it, try to change the code and observe how it is changing the outcome. That way you'll be always getting better idea out of it. So this is all for our this section. We will catch up in our next section. Stay tuned. Hello friends, welcome back to another new section in our Delta Lake journey, and today in this particular video we are going to explore how Delta Lake manages massive metadata available in Delta log directory. So whenever any transaction happens, whether that is insert, update, delete or schema change operation etc., then always transactional logs get created in Delta log location, right? Now suppose you are doing some computation where huge amount of transactional logs are written in Delta Lake. For example, you are restoring a table version to some older version. So that time lot of files might need to be changed, or suppose you are already having an S3 folder where Parquet data are stored. You want to convert that to a Delta Lake. That is converting external data into Delta Lake. That time also huge amount of insert ideally happens. So as a result, during these operations, huge volume of transactional logs get generated in Delta log folder. And we know very well that whenever you try to read the Delta Lake table or Delta Lake data from S3 path, that time first in the backend it goes to Delta log directory. It try to understand the current state, whatever files currently contributing as part of Delta Lake table. From those files alone it provide the data, right? All the files whatever available in Delta Lake are not contributing to the current state. So basically in each read operation, Delta Lake has to segregate those files. It should not read the data from those tombstone files, right? So to understand which files are tombstoned and which are currently contributing in Delta Lake state, it need to scan the complete Delta log folder. There is all these small JSON files, whatever are getting created due to various transactions, it need to read all. And I hope you are getting this, that here also small file problem may appear. Earlier we have observed small file problem with respect to actual data part, whatever is stored outside Delta log directory within our Delta Lake, right? And that time we have taken help of bin packing optimization or z-order optimization to resolve that small file issue with respect to data point of view. But in our transactional log also there are a lot of small JSON files, and there also small file issue might appear, kind of that you can think of. That is, if you try to read the data
from DeltaLake using Spark, it needs to read all those multiple thousands of transactions which are available in small JSON file. Those it need to read and then get the current state data. So that way, obviously, the read operation will not be very useful when you are having massive metadata. And here comes another feature of DeltaLake, using which it can resolve the issue and scale to massive metadata without any problem or decrease in performance. Okay, so that I am going to explain. So just let's have a quick read on these markdown comments. That is, now that we have seen how transactional log records each operation, we can have many very large files with thousands of transactional log entries for a single DeltaLake table, right? How DeltaLake scale its metadata handling without needing to read thousands of small files, which would negatively impact Spark's reading performance. That is what I just now told you, right? That if you are having thousands of small transactional log JSON files, and if you try to read the DeltaLake data, maybe in the backend Spark need to read all those transactions JSON file first to understand the current state data, and that way it will negatively impact Spark performance. Now, what solution DeltaLake is bringing? Let us try to understand. To resolve this particular issue, DeltaLake creates a checkpoint file in Parquet format after it creates by default the 10th commit or 10th transaction. Okay, so what it is doing, basically try to understand as of now, that it creates a checkpoint file, and that file is in Parquet file format. So earlier we have seen only data files are in Parquet file format, whereas transactional logs are in JSON file format. But this checkpoint file is also one kind of transactional file. It is also available within DeltaLog directly, but this will be in Parquet format, not in JSON format. Okay, and it generally creates after the 10th commit by default. Okay, so suppose you have created your DeltaLake and you are continuously performing multiple commits or transactions that can be insert, update, delete, schema change, etc. As soon as 10 commits will happen, it will create a Parquet file, and that is called checkpoint file. And what this checkpoint file will have? These checkpoint files save the entire state of the table at the point in time in native Parquet file format. So what I mean to say is, if I open a diagram, it will be clear to you. So suppose this is a default structure in our DeltaLake location, where suppose my table, that is DeltaLake table name, is the parent folder. Within that we are having _delta_log directory. Within this particular directory we are having transactions, and then outside this DeltaLog directory our actual data in partition format, for example, it is stored. Okay, now first time you have done some transaction, 0.json is created, second time 1.json, third time 2.json, like that. Eventually suppose 10.json is created after our 10th transaction. Now next time if you try to do one more transaction, because 10 transactions are over, it will create this kind of file, that is 10.checkpoint.parquet. And what this file will contain? This will contain the current state of our DeltaLake. That is, after all of these 10 transactions, whatever state the DeltaLake will be having, this checkpoint file will be having same information. Or in another way, I can say that instead of reading all these 10 transaction JSON files just to get current state data, the Spark can only read this checkpoint.parquet file, and it will get the same current state of our DeltaLake. So basically, this checkpoint file have the summary of all its previous transaction, so that it no need to read all the past small JSON files. Only it can read this one, and it will have the same information as if it is reading all the small JSON files. As simple as that. And that's what is written here. These checkpoint files save the entire state of the table at a point in time in native Parquet format, that is quick and easy for any engine to read. Because this time, instead of reading 10 small JSON files, it is only reading one Parquet checkpoint file. Okay, it offers the reader a shortcut to fully reproduce a table state to avoid reprocessing what could be thousands of tiny inefficient JSON files might have. Okay, that is, reading thousands of JSON file is equivalent to reading one single checkpoint Parquet. So this checkpoint Parquet file is having current state of our DeltaLake, kind of summary level information. And when I'll show you the practical, you'll be able to understand that this is only having that currently whatever files are contributing in our DeltaLake, that current snapshot you can understand that way. Okay. Again, I hope you are getting this from this discussion, that it will not help in time travel, because this only store current state information. If you want to do time travel, obviously you might need these small JSON files, but most of the time while working with DeltaLake, using Spark or using Python, we might need to read current state data. So that time this kind of checkpoint file where current snapshot is stored, that can be helpful. Okay, right? And now another important point I would like to highlight. Observe this diagram carefully. Suppose I created my Delta Lake and I have done 7 transactions. So 7.json is created, then another transaction 8.json, another transaction 9.json, another one 10.json, and then when you perform another transaction, then first a checkpoint file get created, that is 10.checkpoint.parquet, and then another transaction will be registered as 11.json. Okay, again it will be starting from 11.json, 12.json, 13.json, like that. Now suppose you have done 12 transactions. So as of now in our Delta Lake, this will be the snapshot that all these files will be available, and using Spark you want to read the data. Okay, so how this Spark will read is basically, it will not read earlier 0.json to 10.json. It will read 10.checkpoint.parquet, which is basically representing the same state as if it is reading 0.json to 10.json, right? And then extra transactions, whatever is not captured in checkpoint.parquet, they are 11.json and 12.json, right? So these two also Spark will read. So suppose as part of our this state, if we want to read the Delta Lake data using Spark, it need to read only these 3 files, because checkpoint.parquet is basically representing the read operation same as of our 0.json to 10.json, and apart from that, these 2 new transactions, these are not available in checkpoint, right? Because checkpoint by default get created with 10 commit interval, right? So maybe by doing continuous transaction, once you reach up to 20.json, post that another checkpoint will be created which will be having complete information till the 20th transaction, like that way. Then we no longer need the previous checkpoint parquet file, that is this 10.checkpoint.parquet, because in 20.checkpoint.parquet already the current state of Delta Lake will be available. So I no need to read this previous checkpoint file also, right? So that way basically Spark works in the backend, and this is how checkpoint help in avoiding read operation for multiple transactions which are stored in small JSON files. I'll show you the practical, that time it will be much clear to you. So here if you see, I am creating a simple Delta Lake. So if I go to my S3 bucket and if I search this particular folder, as of now you can see it is not existing. Okay, so here what we can do, we can create our fresh Delta Lake. Here you can see it is executed, and maybe if we go to our Delta Lake, here you will see ID's data Delta 13 folder is created, and here these all Parquet files are added, and obviously we'll be having one transaction which will basically having the information that this Delta Lake is created, this is its schema, and all these Parquet files will be initially in add state, because we have just added the files. I can download and show you anyway, not a problem. So here you will see all are add activity, 1, 2, 3, then here also, here also, here also. So all are add activity. Okay, cool. So one transaction is created, that is fine. Now I will perform some dummy transaction in our Delta Lake. So first time what I am doing, I am updating the product name for product ID 4, and then I am doing some more update. So here if you see, one transaction, two transaction, and third one we have done. So if I go to my Delta Lake logs and if I refresh, here you will able to see 3 more JSON is created, right? Perfect. Now if I scroll below, I am doing one insert. So I will again execute this one, and here if I go to my Delta Lake, here you will able to see total 5 JSON files are created, out of which 4 are simply insert update just now what we have executed, and first one is for table creation. So total 5 transactions done. Till now here you can see no checkpoint file is there, right? Then I will execute one more insert. So here also it is done. Totally as of now in our Delta Lake 6 transactions available. Then here I am doing 7th one. Then here I am doing 8th one. Then 9th one. So up to 9th one it is created. So if I refresh our Delta Lake, up to 08 JSON is created, starting from 0, that means total 9 transactions are stored, and then here we can perform the 10th one. So 10th one is also done. If I refresh, here as of now you can see starting from 0.json to 9.json, total 10 transactions are stored. Now one more transaction I will simply do. Okay, this is one update activity. This is 11th transaction. Now 10 transactions are over. By default, Delta Lake will be automatically creating a checkpoint file. That is the expectation as per theory. If I refresh here, let's see, and here you will see that our 11th transaction, which is stored in 10.json file, is available. But before that, this beautiful checkpoint.parquet file is created. This checkpoint.parquet file is indicating what? It is basically representing the summary of our DeltaLake snapshot starting from 0.json to 9.json. After performing all these 10 transactions, whatever snapshot or whatever state our DeltaLake will be having, this checkpoint.parquet file will be having same information. That is, checkpoint.parquet file is equivalent to reading all these 10 transactions and getting DeltaLake current state, excluding tombstone files. Okay, right? Cool. I hope you are getting this. If you want, you can read the checkpoint.parquet file to inspect how it is looking like. So here I need to read in Parquet file format because checkpoint is stored in Parquet. And if I want, I can execute .show operation to view the structure of checkpoint file. But in this blue notebook, it is not getting understandable easily. So maybe I will download this Parquet file and I will show in online Parquet viewer. So here I'll be selecting this file. So here you can see our checkpoint file. This is the structure where transaction txn is available. Add, that means add is basically, you can understand, as part of our 10th transaction, what all Parquet files were contributing in our DeltaLake. Okay, this will obviously not help in time travel, but from these add columns, at least if I read only these Parquet files, that is equivalent to previous 10 transactions, whatever we had already done in our DeltaLake, and that way we no need to read the earlier small JSON files. This remove column basically indicating what all files were removed logically, at least, if not physically, from our DeltaLake, right? And those might be available still in our DeltaLake for time travel purpose, but as part of our 10th transaction in the DeltaLake, these all files were kind of removed. Then metadata. Metadata basically contains the schema related to our DeltaLake. So here if I scroll little right more, or maybe I can copy this one and open somewhere here. Here you will be able to see the schema of our DeltaLake, right? As part of our 10th transaction. So if you see the schema here, product ID, then product name, then price, then category, and then updated at, and then discount. This is basically what is our DeltaLake schema as part of 10th transaction. So point to be noted, here I want to highlight this. When I have created my DeltaLake, initially it was having only product ID, product name, price, category, and updated at. It was not having this discount column, right? But where we have added this discount column, if you observe, discount column we have added here as part of one of our transactions, right? And now see the beauty of checkpoint file. As I told you that checkpoint basically have a summary or complete information of all the transactions whatever you have done, and that's how this particular metadata is showing. In our this metadata column, which is basically storing the DeltaLake current state, here the discount column is available, right? So using this, I hope intuitively you are getting that checkpoint is kind of giving the sense of current state, not the history. Okay. And then one more thing, if you see protocol. So what this protocol is basically mean read version 1, mean write version 2. So what this is indicating, you can think of like this way, that DeltaLake continuously release new versions like DeltaLake version 1, DeltaLake version 2, and so on. They are continuously developing. Now to read this particular DeltaLake data, what is the minimum read version for our DeltaLake package it should be having, that is mentioned, minimum read version. And if we want to write the data in this DeltaLake, minimum package version for our DeltaLake what it should be having is 2, version 2. Okay, that is what this protocol is indicating. That is not very much headache for us, but you can focus on these add columns. From this only add columns, DeltaLake will be getting that up to 10th transaction, what all Parquet file it need to read, excluding the tombstone file. So this remover kind of tombstone file with respect to our 10th transaction, only it need to read these few files to get the current state, that is state with respect to 10th transaction. So basically with respect to checkpoint, you need to remember 2-3 points. Number 1, it is created by default with each 10 transactions interval. It is basically kind of having snapshot of our DeltaLake at that particular point of time, like how here it is shown that 10 transactions are over, checkpoint.parquet is created. Now why this feature is available? This feature is available to avoid reading multiple small transactional JSON files. And again, one more point, if you see, the developers have carefully created this checkpoint file in Parquet file format.
right? That is another advantage because Spark works in most optimized way with Parquet file format. So that checkpoint file read operation also happens faster to make sure that the developers have created this checkpoint file in Parquet file format. This is very important point. And if Spark need to read further transactions data, it will not read the data up to 10 transactions. It will start reading from latest checkpoint 10.checkpoint.parquet and then the further transactions whatever is not part of that checkpoint. Okay, and also keep this in mind. If this manner we keep on going up to 20.json, post that another checkpoint will be created which will be having the complete state till 20th transaction. And that time Spark need to read only that checkpoint.parquet file, not this previous checkpoint.parquet file. So in a way, I can say that in our Delta Lake, multiple checkpoints file might be created. The Spark need to refer only the latest checkpoint Parquet file and those transactions whatever happened post our latest checkpoint file. Now I hope you are getting this, that Spark need to track somewhere that what is the latest checkpoint, correct? Because as of now in our this Delta Lake only one checkpoint Parquet file is available, so it can easily understand this one. But eventually with more transactions, multiple checkpoints file might be created, but Spark need to refer only the latest checkpoint file to get the current state of Delta Lake. For that, there is one more file created which is called last checkpoint. If you download this one, you will able to see clearly that it is having this information that this is the latest checkpoint. That is, Spark need to read this last checkpoint file also to understand what is the latest checkpoint available in our Delta Lake. So that let me show you. Here if you see, clearly it is having the version number 10. That means it need to read the 10.checkpoint.parquet. Eventually with transactions, if one more checkpoint get created, that can have version number 20 by default, because by default with 10 transaction interval the checkpoint file get created. And rest all schema related information or metadata information like size in bytes, number of add files, that is as of now currently in our Delta Lake, how many files are contributing, all these informations are available. And one more key I want to highlight, that is checksum. Checksum is basically having this unique value and its importance is same like how we generally have in other use cases, that is it makes sure that the file is not getting corrupted, kind of a hash value is stored for future reference, right? So this last checkpoint file is also very important. I hope you are getting this overall how the checkpoint is working. And now I want to show you how you can control the generation of checkpoint file. That is, if you don't want to create checkpoint files with 10 transaction interval, maybe you want to do with 2 or 3 transaction interval, that also you can do. So let me show you that. So I'll be going back to my Delta Lake, and here if I scroll below, here at this point we will explore, that is controlling the checkpoint interval. So let's see how we can do that. So here what I am doing, I am creating a Delta Lake table with the name Delta Table 14 with this location IDs data Delta 14. Okay, if I search here, as of now it is not there. All we need to do is configure this property, that is table properties delta.checkpoint interval. And here you can mention the interval with which you want to create your Delta Lake checkpoint. So here I am mentioning 5. That means with each 5 transaction interval in our Delta Lake checkpoint file will be created. Okay, which will be having snapshot of our current Delta Lake state. Instead of reading all past 5 transactions, we can read only the latest checkpoint that will be created. So here I can run this one. So here it is created. If I refresh and search for our new folder, here you will able to see that this new Delta Lake is created, whereas in our Delta log 0.json is available. But in data, if you see, no data files, no Parquet data files are available, right? And that is pretty much obvious because we just created a table. This create operation is one transaction that got tracked in this 0.json. But there is no data in our Delta Lake table, that's why no Parquet file is available. As simple as that. Okay. Now we are doing an insert activity. So this insert activity is second transaction in our Delta Lake. First one was create table command, right? So due to this insert, here this time we will able to see some data files, but let's focus on our transactional log. Our second transaction is created. Then here we are doing one more third transaction. If I refresh, here third transaction file is created. Then I am doing fourth one and fifth one. Okay. So here 5 transactions are created. If I refresh, 1, 2, 3, 4, 5 transaction files are created. All are small JSON files. Now I will do one more transaction. Okay, and the expectation is automatically that last underscore checkpoint file should be created and one checkpoint.parquet file should be created, because here we have defined that the checkpoint file should be created with 5 transaction interval instead of 10. So let's see that whether it is happening or not. So I will run this one, and here this is our 6th transaction basically. If I refresh, here you will able to see the last checkpoint file, along with that 5.checkpoint.parquet file is also. Okay, and our new transaction got registered also. Okay, right? So DeltaLake automatically in the backend is creating this checkpoint file. We no need to do anything. That is one point. And if you maybe download this particular last checkpoint, you will see it will be having version 5. Here you will be able to see version 5, right? So last checkpoint's importance is it basically keeps a track that is which checkpoint.parquet file is the latest one. Okay, right? And even if you download this checkpoint.parquet file, you will observe the summary of it. Maybe I can refresh this screen and upload this Parquet file. So here only Parquet files are added, which is pretty much obvious because in our DeltaLake we just executed insert. There is no remove thing. Metadata is having the schema of our latest DeltaLake at the time of 5th transaction, and protocol is in read version, in write version, to avoid any conflict with latest DeltaLake module. Kind of backward compatibility, forward compatibility, that kind of thing you can think. Okay, right? So this is how DeltaLake handle massive metadata or DeltaLake scale while having massive metadata in our DeltaLog folder. That is, when you try to read the data using Spark, it never read individual small JSON files. It just read the latest checkpoint, and after that whatever transactions are there, those happen. Right? I hope you understood this. Try to do this experiment in your own DeltaLake. You will be getting much more better idea out of it. And if you have any doubt at any point of time, you just mention in the comment section that specific timestamp and what doubt you are having. I will try to reply back quickly. This is all for this section. We will catch up in our next section. Stay tuned. Hello friends, welcome back to another new section in our DeltaLake journey, and today we are going to explore the concept around deletion of log files beyond a certain retention period. So this particular concept kind of having little bit similarity with respect to vacuum command concept and the very important delta property, that is delta.deleted file retention duration, which I have already covered in my previous section. So let us try to understand log file deletion beyond a certain retention duration. So suppose I am having a DeltaLake table with the parent folder name my table, within which our default structure is available. That is, there is a folder called _delta_log, within which all the transactional informations are available. And here suppose outside DeltaLog directory, our actual data files in Parquet file format available. Now suppose you have continuously done lot of transaction. Post 10th transaction 10.checkpoint.parquet file is created, which I have covered in my previous section, right? That this basically helps in reading our DeltaLake faster. Instead of reading all these small transactional JSON files, if we read only this checkpoint.parquet, from here itself Spark will get the latest state of DeltaLake. Okay, so suppose initially when we created our DeltaLake, file 1.parquet was there, and then with successive transaction file 2.parquet is added, and file 3.parquet is added, and maybe file 1.parquet is removed in some transaction. That means it became tombstone file. But immediately, obviously, it will not be deleted because DeltaLake has time travel support. So as a result, immediately physical delete does not happen. It only logically deletes the file. Still in our S3 location, the file is available. And beyond a certain duration that is configured using delta.deleted file retention duration, using this property, I can configure whether it is 1 week, 2 weeks, 200 days, 500 days, like that. And beyond that date, this file can be deleted, and that also not automatically. Using vacuum command, we can basically delete this unused tombstone file, right? So this concept is pretty much known to us. But if you recall, one very important point I discussed while covering vacuum command, and that is vacuum command only play with data files, not our transaction files. So as a result, even if due to execution of vacuum command some files are deleted from our DeltaLake, if you execute the history command, you will still able to see the traces of those files, that those files are available in history command. That way it will show, right? And the reason is pretty much simple. When you execute history command, it goes to DeltaLog directory to generate all the historical transactions whatever done in our lakehouse. And vacuum command is not going to touch our transactional logs. As a result, in history command you can see everything, right? Now here is the important point comes into picture. That is why you started using vacuum command. The reason is storage cost, right? That is obviously all the unused tombstone file we can keep in our Delta Lake for infinite duration for time travel purpose. But if we follow that pattern, storage cost will increase because these unused files will be there, right? If you try to map that same pattern in our transactional log directory, here you will observe that same kind of issue is happening. That is, here all the small transactions are there. That is totally fine. But once the checkpoint.parquet file is created, this is having basically the latest state of our Delta Lake. What all files are contributing to our Delta Lake, that information is available only in this particular transactional log itself, right? But still we are keeping all these small JSON files. The only reason is using checkpoint file you cannot perform time travel because it only gives you the latest state. In each different versions, how it is changing, what all file adding, what all file deleting, it will not show you that. So using checkpoint you cannot perform time travel, and that is the major reason we are still keeping the small JSON files even after this checkpoint file creation, so that time travel can be done. But here also that same problem of storage cost might appear. Suppose you are having thousands of small transactional JSON files, obviously it will keep on increase your storage cost by a good amount, whether you are storing the data in S3 or Azure blob storage, etc. So here also we might need to have a trade-off, that how much time travel I want to do, and beyond that also if it is going, we can delete these unused transactional files because the state is anyway stored in checkpoint file, so we can only rely on that, right? So here comes the deletion log file concept, okay, and that is controlled by this property, delta.log retention duration. So earlier, while discussing the concept of vacuum command, we have explored delta.deleted file retention duration. This property is basically defining what is the retention duration for this unused tombstone file, right? Similarly, this log retention duration basically defines what should be the retention duration of these small transactional JSON files. And that retention duration starts once our checkpoint.parquet file is created for those transactional logs. That is, suppose we are having these transactions, and as soon as checkpoint.parquet file is created, these all JSON files are kind of no longer required. Only they are kept for time travel purpose. So that time their retention duration starts. And if you are keeping this particular property, log retention duration, by default which is 30 days. So what will happen ideally, once checkpoint file is created, after 30 days, these transactional files no longer need to be kept in our Delta Lake system. They can be deleted. That way obviously we will be having time travel compromisation, but it will help us in reducing the storage cost. As simple as that. So each time a checkpoint is written, Databricks or our any Delta Lake platform automatically cleans up the log files older than log retention duration. So suppose 10.json is there and just now this checkpoint.parquet file is created. So that means these are kind of became tombstone transaction, and beyond 30 days these can be deleted. Now you might ask that like vacuum command, is there certain commands which we need to execute to delete these tombstone transactional logs beyond retention period? The answer is no. It happens automatically. Delta Lake automatically does that depending on the configuration of log retention duration. How it automatically create the checkpoint.parquet or last checkpoint file. Similarly, automatically it does the delta log cleanup. And obviously, I hope you are getting this, that if these transactional logs get deleted, then you cannot perform time travel. So time travel, how much you can do, that is controlled by two things. One is presence of these transactional logs, small JSON files, as well as presence of the data files, right? So I can say in other way, not only time travel is controlled by deleted file retention duration, but it is also dependent on log retention duration. Suppose deleted file retention duration is 200 days, but log retention duration is only 7 days. And suppose your checkpoint is created after that 7 days is over. So automatically these small logs will be deleted, right? So even if your data file is available he will not able to go to that old state because those state itself are deleted because transactional logs are deleted, right? So that's what here I have written, that delta.log retention duration as well as delta.deleted file retention duration both impact time travel. And here is a pretty much obvious question. Suppose I need to perform time travel up to 200 days. Then I need to make sure that the tombstone data files are also available for 200 days as well as all the transactional logs also available for 200 days. So if I need time travel up to 200 days while creating the delta table, I need to make sure both of these configuration we are making 200, right? Very important concept. I hope you are getting this. Related to this particular concept, whatever theoretical blogs you might need to refer, all those I'll be providing in the description box. Just go through that, understand this concept, very vital property with respect to our delta table. And if you have any doubt in this particular discussion, feel free to ask this in the comment section. I'll try to reply back ASAP. We'll catch up in our next section with some other interesting concept related to Delta Lake. Stay tuned. Welcome back to another new section in our Delta Lake journey. And this is the last important topic what we are going to cover as part of this particular Delta Lake course, and that is change data feed, or maybe in popular terms we also know this concept as change data capture or CDC. That is like DynamoDB stream or Snowflake stream, Delta Lake also having support for change data capture, and that is called as CDA for change data feed. Okay, so how to do that, how we can read the change data starting from a specific timestamp or version, that we are going to explore in this particular section with practical example. Okay, so to implement change data feed on any Delta Lake table, you have to configure this property delta.enable change data feed true. Okay, and I am creating a fresh delta table in this particular folder. So as of now, if you see in our bucket, if I just do a Control F and search, here that particular folder is not available. So I will run this one, but before that, first let me run the first cell. So here Delta Lake configuration is done, and now I will go back to this particular cell to create my delta table. So it is going to create this Spark session. First cell execution is going to take obviously some time. And once this particular delta table is created, we are going to insert some data in this table using this simple insert command. Okay, so before that, what I can do here, I can execute this select query just to show you that initially data is empty in this table, sales data demo YT. So we'll execute once the first cell execution is done. So session has been created. Now it is executing this particular query. So we can hope that with this particular folder now in this specific location, folder will be created, and here you can see incremental test YT. If we go inside that, as of now, because there is no data, only delta log folder is available, within which we will be having only one single JSON, which is indicating the table is created, right? So yeah, this cell execution is complete. Now if I execute select start on this table, you will see initially it is having empty data. Cool. Now suppose I am executing an insert command in it. Okay, I hope this fine up to this. So 2 rows we are inserting, and now what we will do, we'll try to implement CDC or get the change data. So just like in Snowflake, what we generally do, that we get the change data starting from a specific timestamp. Because we are starting for the first time, so we can consider the start time as a very old value so that we can get the complete history, and generally we consider that as 1971 January at 0 AM, right? And this is how you can extract the change data from Delta Lake table. That is spark.read.format delta up to this it is same, and then we generally execute .load to read the Delta Lake location. Only 2 things what we need to add is read change feed true. So I want to read only the change data, and starting from what timestamp I want to read, that I need to provide. So this is generally in UTC timestamp. Start timestamp, I am giving this particular value because this is the first time we are extracting the change data. So kind of complete history I want to get, you can think that way. And if I do df.show, here you will see that it will show you that these 2 insert queries are executed. That means they are the changed records starting from table creation. And here beautifully you can see these are the informations what we are getting after reading the change date. So ID, product, quantity, price. These are the default column informations whatever already we are having in our table. Apart from that, we are having some metadata columns just like in Snowflake streaming, like change type, insert. So insert, update, delete, what kind of activity we are doing for which data is getting changed, those informations we will be getting in this column. Then commit version, this is integer column, and already we have discussed several times that whenever you perform any transaction in your Delta Lake, one incremented commit version gets created. So this particular rows got changed. In which commit version, that if you want to know, you can refer this commit version. And when that commit happened, if you want to know that you can check in commit timestamp, which is basically UTC timestamp. Okay, right? So I hope this particular structure of change data feed is clear to you. Now if I do select start from this particular table, as of now here you can see that we'll be having only 2 rows, whatever we have inserted. Now before making further changes in our Delta Lake table, I will capture current timestamp in UTC. So I can execute select current timestamp. I have captured this timestamp so that next time when I will try to capture the change feed, I can extract the feed from this specific timestamp instead of starting from some very old value. Okay. Now here what we are doing, we are updating for row ID 1 price equal to 1100. So here let the cell get executed. One row is affected, which is obvious because ID 1 only one row we are having. Earlier the value was 1200, now it is 1100, right? So if I do select start from this particular table again, here you will see for ID 1 the price became 1100, right? Perfectly fine. Our transactions are working. Now suppose starting from this specific timestamp, what all changes happened in our Delta Lake, that if we want to understand. So that time that same code you can use. All you have to do is change the start timestamp equal to this particular value. Okay, that is spark.read.format delta read change feed true option start timestamp, and I want to get all the changed rows starting from this specific timestamp. That means after this timestamp we just executed one update command, right? So this information we should be getting as part of change data captured. And rest part is same. I am just executing df.show to get the view of our change data. So I'll run this one. And here you can see we are getting 2 rows. Okay. Although we have executed only one update statement starting from this specific timestamp, but we are getting 2 rows here in the output. Try to understand, it is just like DynamoDB stream, that whenever you execute update command against your Delta Lake, in change data feed, it captured the pre-image and post-image both. That is before the update what is the row snapshot it was having, and after the update what is the row snapshot we are having. That it captures. So here if you see, earlier for this ID 1, product is anyway laptop and quantity is 5, but price was 1200, right? So this is the old image. So that's why if you see the change type, here you can see it is written update pre-image. Pre-image means before update command what is the row image was having, that it is depicting. And commit version 2. So commit version 0 was basically kind of when the table is created. Commit version 1 is kind of when we executed this insert command. And in our third transaction, we are executing an update that is getting captured in commit version 2. That is basically same concept in each transaction. Commit version is getting incremented by value 1, right? And commit timestamp also it is capturing. The most important part here is change type. It is capturing pre-image, before update what is the image, and post update what is the image, that it is capturing in update underscore post image. So here if you see this particular row, this is the current state in our Delta Lake table for row ID 1. That is how it is capturing update thing. Okay, right? Now I will show you a demo with delete thing. So again I will capture the UTC timestamp, and suppose this is the one. Okay, and then what I will do, I'll execute an delete statement, and I want to capture all the changes whatever happened after this specific timestamp. Okay, what we have done, we have deleted the ID2. Okay, so as per our this particular table, if you are deleting ID2, we'll be having only this row ID1 product laptop quantity 5 price 1100, right? So maybe that one I can show you also using a select statement percentage SQL select star from sales data demo YT. Okay, so if I run this one, here you will see that only ID1 is available. Perfectly fine. But suppose I want to capture what all data got changed starting from this specific timestamp, right? That is only the delete statement it should highlight. That let's see. So here I will copy this specific UTC timestamp, and in the same code I'll be updating that here, and rest part is same. And if we run this one, if we try to read the change data, here you will see that it is clearly indicating that after this timestamp, only change in our Delta Lake is ID2 is deleted, and commit version is now 3, right? Again it got incremented by value 1 and change type is delete. So using change type column you can understand whether it is getting inserted, deleted, or if it is updated. Two different change type you might get. One is update pre-image, one is update post-image, commit version, commit timestamp, all this information you will be getting. Okay, right? So this is the major concept of change data feed in Delta Lake. You can now utilize this particular concept to build your own data pipeline. That I am not going to cover. Based on your business requirement, you can apply this concept. But one important point what I want to highlight is what is happening in the back end for our Delta Lake, how it is tracking change data feed, right? So here if I refresh this particular screen, where our Delta Lake is having, here you will see that data files are available, Delta logs are capturing all the transactions. Up to this it is totally fine. But one new folder is created which is called _change_data. Okay, and here is all our change data gets captured in Parquet file format. So maybe I can show you this also by reading this specific location. So here I am reading the data in Parquet file format because our change data, if you observe, they are getting stored in snappy.parquet. So Parquet file format is needed, and if I execute df.show, here you will see all the change operations, whatever we have done, that Delta Lake is basically storing in this specific location. Okay, point to be noted, this is not storing only metadata, this is storing complete information. Like here you can see the data also, right? ID, product, quantity, price. So generally Delta log store only whatever Parquet file added, deleted, or updated, etc., etc. But to capture the change data in the backend, Delta Lake is not only storing the metadata information like change type, but it is storing copy of actual data also, that how it is getting changed. And here you will see that only update and delete informations are available. Although we have made one-time insert, then update, then delete, but insert don't get captured. And intuitively you can understand this very easily that in this specific change data, I don't want to store unnecessary data points which I can derive somehow. Because this change data folder not only storing metadata, it also store data as well. So this particular folder may incur huge cost with time, right? So Delta Lake try to minimize the data copy information in change data and try to reduce that as much as possible. Now suppose due to insert one specific Parquet file is added in our Delta Lake, that information very easily we can get from the Delta log transactional logs. We may not need to copy the complete data separately in another folder. That is why only update and delete is getting captured in the change data folder. What is not very easily can be captured from the transactional logs. But if it is a completely insertion of a new file, then that can be easily extracted from transactional logs. That's why Delta Lake intelligently excluding insert cases in the change data folder, so that way unnecessary data copy no need to have in our cloud storage, and that way it can save cost. That is how maybe intuitively I hope you are getting that. That is why it is not capturing insert thing. But overall, this is how change data capture is working. That there is a new folder change_data where it keep a complete copy. Whatever data gets continuously changed, right? I hope you got some intuition around the implementation of change data feed or change data capture in Delta Lake. So this is all for my this specific course or video, you can say. I tried to cover all the important concepts around Delta Lake. Obviously, this is not the end of Delta Lake concepts. There are some more which maybe sometime later I may cover in Databricks notebook or in some other cloud also, like Snowflake, etc. But I can tell you for sure, whatever concepts I have covered till now in Delta Lake, starting from very simple insert, update, delete, then vacuum command, then conversion of Parquet to Delta, restoring table, optimization, bin packing optimization, z-order optimization, schema evaluation, then DeltaSpark module, DeltaLake RS module, which is native to Python, right? So if you at least go through all these concepts, try to do some hands-on, then surely you will have a solid base for your Delta Lake journey. Complete notebook, all the reference links I'll be providing in the description box. If you have any doubt at any point of time, please feel free to ask that. I will surely try to reply. And if you find this video helpful, then please like, share and comment. Subscribe our channel if you have not subscribed till now. And don't forget to press the bell icon to get the notification of our latest videos. Thank you for watching.